So the first, uh, so the first, uh, the first two talks we have are about from Andy Halterman. They're about event detection for protest events, and we will listen two talks from him. Then the session finishes with a discussion on ethical issues, and we have one more talk in the middle. So let's give the word to Mr. Halterman about who tell us about the protest events, and it will be two talks on this topic.
Okay, great. Can you all see me and hear me?
Yep.
Yes. It's visible.
Okay. So I'm going to give two talks in a row, but they're two separate projects with two separate groups of collaborators. So we'll have a sort of pause and switch in between. So the first project I'm going to talk about is with Ben Radford, who's a fellow political scientist who works on event data as I do. This paper is a short paper that's in the findings of ACL, and it's a crossover with the case workshop, which is great because we're really hoping to get feedback from people about where this could go in the future and other applications for what we talk about. I see Ben. Hi, Ben. So the motivation for this project is something that we noticed sometimes in our own social science work, which is that oftentimes we'd like to train a classifier or a model to do a fine-grained task, but the labels that we have to train a supervised model are only available at a coarser level of resolution. And so what we mean by this is we use an example from the Crowd Counting Consortium, which is a group that collects data on protests in the United States. And they provide information, so along with the raw text, they'll report a coarse label, so basically the order of magnitude of the protest size. And they'll also report a gold span, so the precise phrase that describes how many people were at the protest. And we wanted to use this data essentially as training data to see if we only had access to this coarse label, so essentially the order of magnitude of the size of the protest, can we train a model to recover the gold span that they also provide? And so just looking at this example document here, you can see why this is potentially a difficult task. So we have a lot of different numbers in here. It's hard to do this with just regular expressions or some simple way. And so we really want some more sophisticated model that can learn to identify the phrase given only the order of magnitude. And just to start with, I think what the main contributions of this paper are. First, we provide a new formulation of this task. So this, what we call an upsampling task, going from coarse labels to train a fine-grained model. So going from order of magnitude labeled data to extracting the phrase that describes the size of the protest. And we provide a data set that other researchers can use to build on. Second, we provide some baseline models. So both rule-based models that use dependency parsings and regular expressions, and also zero-shot QA models to see how well those perform on this task. And then finally, we introduce a new multitask model that does somewhat better than the baselines. But I think, again, we'd like to emphasize, we're hoping people will use this data to build on the baselines that we provide here. So here's a table from the paper that gives a little bit of information about how the different baseline models do. And what we mean by exact match here is, does it recover the exact words that the Crowd Counting Consortium reports when they're hand annotating these documents to say, here's the phrase that describes how many people were at the protest. So this is the percentage of time that each of these models recovers the exact phrase. The F1 here is the token level F1. So if there's a partial overlap, there's some credit for that. The heuristic rules model, there are more details in the paper, of course, but essentially, this is a combination of keywords and dependency rules. So we look for sentences that have a small set of keywords like crowd or protesters or gathered. And then we we find number words and expand out the phrase to include adjectives and make sure that we're getting the whole phrase so that we're matching what the crowd counting consortium reports. So this does fairly well, actually. We're getting it right about half the time. The second baseline model that we use is a Roberta model that was fine-tuned on Squad 2. So if you were at Liza's opening keynote, you heard about how well these QA models work for event extraction. So here we're giving it the document and asking how many people were at the protest. It hasn't been fine-tuned on any data except the Squad 2 data that it was originally fine-tuned on, and it performs much less well. So after doing these baseline models, we then introduce a multitask model of our own. So here's the architecture of the model. And basically this is doing two things. On the left side here, it's doing something similar to what a Squad 2 QA type model would do, which is it's trying to predict the beginning token and the end token that answers the question, how many people were at the protest? But we also wanted a way of using the course information, since that was our whole objective. So how do we start with sort of a larger corpus of articles where we know the order of magnitude, but not the exact size, and use that to inform the extraction. And so the setup that we use here is we split our training data into two parts. We have a very small number where the exact gold span is provided, so what the exact correct answer phrase is. So we have 25 of those. And then we have a larger set of a couple thousand where we have the order of magnitude of the protest. And what this part of the model on the right is doing is essentially using the attention in the normal sort of QA type approach to inform a second model that's trying to predict the order of magnitude. So we're essentially using the attention here to focus on a particular phrase and then apply a classifier on that phrase to predict the order of magnitude of the protest size. So to make that a little bit more concrete, here's what that looks like. So we're the first two rows are predicting the beginning of the span and the end of the span. So it's looking pretty good here. And then the second one is for the course label task. So it's using essentially the cumulative product of these two, sort of the start going forward, the end going backward, as essentially an attention mask that will allow us to focus on one particular part of the document. And then we apply the classifier to say, around 10 to 50 looks like what the crowd counting consortium calls the size category 1. Once we do this, we have a few different results. So the gold spans is on just those 25 examples where we have the full, this is the correct span. And fine-tuning the Roberta QA model on just those 25 does pretty well. So we only need to give it 25 examples for it to learn fairly well how things, sort of where in the document to look. The second row is when it has access to no gold spans, only to the course labels. So it's trying to predict the document level order of magnitude without any access to the fine-grained labels. And then this final one is a hybrid system where we augment the data using some rules to try to say, soft label or distantly label some gold spans to train on, and we get some extra performance benefit from that. So the code is available on Ben's GitHub. We don't have the raw text posted for copyright reasons, but we can share that with researchers. So anyone who's here, we can provide the raw text for. The paper with more details is available here. And specifically, we have more details on the baselines and how the proposed model works. We have a section about the ethics and impacts of studying protests in this way. And we suggest some other applications in social science that a model like this could be useful for. So I think with that, we have a little bit for questions, and we're excited to hear what you have. And Ben is also here and can answer questions as well.
Thank you for this inspiring talk, inspirational talk. Mr. Radford, Benjamin Radford. Benjamin, you're going to give a question?
Oh, sorry. No, I was clapping for my co-author. Sorry.
Yeah. Okay. Any other questions? Any questions on the presentation? Or?
There's one question in the chat. I think Sebastian asks, did you consider hand labeling more samples with gold spans? Andy, do you have a thought on that?
I think I maybe didn't explain this as well as I could have. So we actually have gold spans on every article in the corpus because the Crowd County Consortium provides that as part of their data set. In this restricted setup, we only gave ourselves access to 25 because I think we wanted this to more closely match a social science setup where you might have a lot of sort of coarsely labeled documents because those are often cheap to get, or you can find existing annotations, and maybe people will annotate a small number themselves. That was the situation where we had access to 25. So we could have had access to 6,000 or so, but we only gave ourselves access to 25.
Yeah, to build on that just a little bit. So it feels a little contrived because we're hiding a bunch of gold spans, actual ground truth data from ourselves. But like Andy said, part of the motivation for that is we wanted to evaluate whether or not this is possible because there are other settings in which those gold spans are just totally unavailable. For example, you sometimes will see this when you're trying when you're looking at data on things like battles and conflicts where you have casualties that are measured in orders of magnitude in data sets, but you could potentially collect, better kind of firsthand accounts in which you could get better estimates. And so we wanted to know if we could use this type of a technique to then go back to the raw accounts and extract better data from the more coarsely hand-coded data that are usually coded by like undergraduates, for example. And so they're like 3 categories and that's it.
I actually wanted to ask a question. How much data did you use? These results you're reporting on how much data they're based?
So we had
how many documents?
So we had about 6,000 documents where we were able to record the full text.
That's pretty many. These are pretty many. The results come to me are good. Like over 60% already in this in argument detection. It is already a result which is serious. Nikolaos Stoer.
Yeah, hi. Thanks. Yeah, thanks for the nice talk. I think I sent you an email previously already. So yeah, I really like this direction because we're trying also to extract more numbers beyond fatality counts only, because we reckon that like most data sets have the fatality numbers annotated, but not anything else. So I was just wondering 2 things. The one thing is I noticed that you filtered all the data and only included those news reports where the exact numbers were included, right? And so I was wondering if you also tried going beyond that, including like spelled out numerals, stuff like a dozen, hundreds. And the other thing, if you also try to go beyond protest counts. So basically because like I figure this task is getting really hard if you try to do some kind of semantic resolution of trying whether these are protesters or people who got kidnapped, injured, etc. If you discovered or explored these 2 directions.
Yeah, so we were a little bit leery of trying to expand the words out because most of these documents will have maybe up to a dozen numbers mentioned in the article, and so we didn't want a situation where we were looking too hard for a match because we didn't want to have a false positive match, where it says hundreds of people were at the protest versus hundreds of people have been detained at the border, and that's what the protest is about. So we wanted to make sure that we weren't mislabeling spans, but it's possible, especially with some more hand annotation, that we could get there. On your other question about looking for other kinds of numbers, we had looked initially at trying to get the number of people arrested, which Crowd County Consortium also reports, but that data was much sparser. but I think that would be I think we wanted to go there, and we just didn't. So we encourage other people to use our data and go there.
Cool, thanks.
Okay, well, I think we're probably out of time.
I think you can jump to the next talk.
Okay. Sorry, I just have to get my other one. Okay, so this is separate work. This is work with Brendan, who's here, and I think Katie and Sheikh, who might not be here unless they just came in. And this is also work that's appearing in the findings of ACL. And once again, we're excited to have feedback here, and we hope that people will work with the data that we've developed on this project. So just to start with what the main takeaways are of this project, we introduce a new data set that has some novel features that I'll describe in a moment. But essentially, we're providing complete natural language annotations on a large corpus of events or large corpus of text, where we annotate every instance of the event classes that we're interested in. And this has some really nice benefits that we'll talk about. We also introduce some new tasks and evaluation techniques that are motivated by the way that social scientists use event data that we think will help spur more development of good event extraction techniques in computer science. And finally, we provide some zero-shot baseline models, including entailment models for event coding that I think are a new approach to event coding that has some promise. The data and the paper are available at this link, and we hope you'll take a look. So the primary motivation for our project is that current event data sets don't let researchers evaluate the recall of their event data systems, and they don't have good evaluations against aggregate measures of political events. So we have a lot of different event data sets that we can draw on that are in some ways either very focused or very general. And I think at this workshop we're all interested in being able to aggregate political behaviors from text or extract events from text and use these for downstream tasks. And there's not currently a good way of evaluating how well we do in specific ways. So on one hand, we have data sets like ACE, FrameNet, MOOC or MUC. I'm not sure I don't think I've ever said it out loud, that are really nice in that they provide very fine-grained annotations of different arguments for events. But these documents are often an unrepresentative sample. They're certainly not a comprehensive set of documents. And it's difficult to go from performance on a data set like ACE to knowing how well we perform on the objective that ultimately we really care about, which is understanding at a high level the different behaviors and actions that political actors are taking. On the other side, there's some data sets that are very macro. So they might annotate every document or provide machine codings on every document, but we don't know how accurate they are. So things like IQs or GDELT, or hand-coded things like ACLID or GED. And in this work, we're trying to be in the middle by collecting annotations sort of on a limited set of documents, but annotating every single document in that corpus. So first, I'd like to talk about the new data that we're collecting. And I think this has three features that make it unique. The first is that we have a completely annotated corpus. So we take every article from the Times of India published in March 2002. And we focus specifically on this because this was a period of severe communal violence in India, with violence occurring between Hindus and Muslims after some violence that occurred after a pilgrimage. So this is a period of time that political scientists are very interested in, and several people have made hand-coded event data sets studying behaviors like this. And so there's some useful social science motivations for why we focus on this. We do some filtering, so we reduce the corpus to about a third based on some place name keywords, which is a fairly standard technique in political science. And from this resulting set, we have about 1,200 stories and 21,000 sentences. And we collect annotations on every single one of these sentences, so that we can have essentially a completely annotated corpus. So what do these annotations look like? So we focus on the actions taken by Indian police in the context of communal violence during this 1 month period. We use a set of trained annotators that are political science majors or undergrads that we've worked with for about 6 months. And we made a few decisions that I think are slightly different from the way that previous annotations have been collected. The first is that we, following some recent work in the past year, we collect annotations on event types in the form of Boolean questions. So we ask questions like, did police kill someone? Did police arrest someone? And then some other ones that I think are of particular interest to social scientists, like, did police fail to act or not intervene? Which is consequential for theories about how the state intervenes in these instances of communal violence. Some other unique features are we collect sentence level annotations, but within the broader context of the document. So on the right here, you can see sort of a mock-up of what the interface looks like, where they can see the entire document. And then we ask them about one specific sentence within that document. 2 people died in police firing and another 3 were injured in the shooting. And they check which of the questions are answered yes by this sentence. So what that looks like in terms of semantic event types are we collect annotations on these 5 semantic event types using the Boolean questions that you saw on the previous slide. And I think what you can see from this is that it's fairly sparse. So out of the 21,000 sentences, 96 describe an instance where police are using lethal force. So yeah, and I think one last important thing to mention on this is by annotating every single sentence within this corpus, we can now evaluate recall for potentially the first time with event data sets. So we can, it's fairly easy to look at the precision of extracted events. You can look at it and see if it makes sense, but it's very hard to estimate the recall because we don't have annotations on every single document within a corpus. And so by collecting this information over every sentence and document in our corpus, we can evaluate the recall of our event extraction systems. So having collected this data, we then turn to 3 different tasks, each of which is motivated by the interests and uses that these can be put to in social science. The first task is a sentence classification task. And as I mentioned before, the way that we do this sentence classification task is to use a 0-shot model where we're taking a transformer model that's been fine-tuned on the MNLI data set, so this entailment data set, and we're using this to code our events for us. So what's going on here is we give it a context like the one on the right. So a sentence like, police officials said that nearly 2,537 people so far have been rounded up in the state. And then on the right side, we give it a declarative form of the questions that we use in the annotation. So we give it the statement, police arrested someone. And what this Roberta model that's been fine-tuned on MNLI does is it will return essentially one of 3 classes, whether that statement is entailed by the context, whether it's contradicted by the context, or whether it's neutral or irrelevant. And we believe this is the first time that people have used an entailment type setup to do event coding, and we found that it was a pretty useful technique for what we did. So looking at the 0-shot model results at the sentence and document level, so we have here each of our 5 semantic event types. And we have here 2 zero-shot models. So one of them is sort of a pseudo zero-shot model. It's a keyword-based model where we, based on social science expertise and some keyword expansion techniques, come up with keywords to try to code each of these semantic event types. So here's the F1 score. So obviously higher is better. We then compare this to the zero-shot Roberta plus MNLI model, where we're giving it a statement like police killed someone, police arrested someone, police failed to act. And then we can compare that to the gold standard annotations that we've collected from our annotators. And we find that the zero-shot Roberta MNLI model is remarkably good at identifying some of these event classes. We think that these sorts of models are promising for future event extraction work. So that's one task that we applied, one task that we used our data for, so looking at sentence level classification. A second task was a document ranking task. And we have a discussion in the paper about why this is often useful for social scientists who may not want ultimately to use machine-coded events, but are interested in using event extraction models as a way of surfacing documents that they then read and code qualitatively by hand. So here's a table of results looking at again, 3 zero-shot models. I'll move a little bit quickly over this, but we're looking at 3 models here, a standard BM25 model, a model that's Electra that's been fine-tuned on the MS Marco data sets. There's a search engine data set. And then finally on the right, the same Roberta MNLI model. And what we report here is average precision, which is a standard measure in information retrieval. We then also report a new metric that we call proportion read, or proportion read at recall X, that I'll talk a little bit more about here. So we introduced this new metric, proportion read at recall X, to reflect one of the tasks that social scientists have when they're looking for events in their corpus. And essentially what this metric reports is the proportion of the ranked corpus that a researcher would need to read to find a specified proportion of relevant events. So if we have a model that we can use to rank documents, either by predictive probability or a ranking model, if we started reading those ranked documents, how many of those documents would we have to read to find, to reach a certain level of recall? So in this case, a 95% recall, so we recover 95% of the relevant events. And we find that this zero-shot Roberta MNLI model can greatly reduce how many documents from a corpus a researcher needs to read. So after ranking the documents using the model, if we're predicting the arrest event, a researcher would only need to read 17% of the documents to find 95% of the arrest events. And we think that this metric is useful, I think because it aligns so well with the objectives that a lot of social scientists have, which is not necessarily to produce a final event data set in a fully automated way, but to search for particular instances of events that they can read them by hand and conduct qualitative analysis. The final task that we look at is a task that we call social aggregates or temporal aggregates. Because ultimately what we care about as social scientists is how well this recovers aggregate trends over time out of the corpus in order to match what's going on in the real world. And so in the paper, we provide some comparisons between the gold standard annotations that we collect from our annotators, the keyword matching technique, and the same zero-shot model that we've used in the previous tasks. And so this figure is showing you one of the semantic event classes that I think is particularly interesting, which is the failure to act event type. So police are reported to stand by and watch or neglect to intervene. And what we can see here is that the keyword matching technique gives us a very different perspective of what's going on than we would get if we'd actually read all the documents. And the Roberta MNLI model here is performing much better, but it's still not totally matching what the gold standard annotations are. I think, and we thought this was important to provide as essentially a semi-extrinsic evaluation of our models. So if we know what happened in the real world, how would our understanding be different if we had used each of these different techniques? And again, we find this MNLI technique is useful, but there's still room to go. So just to return to our main takeaways here, we have three main contributions. So we introduce a new data set with high quality annotations of event classes on every sentence in our corpus. And this allows us to estimate for the first time the recall of event extraction models. Second, we provide some social science motivated tasks and evaluations. One of these consists of whether we can identify all instances of a political event. And we introduce a new recall focused evaluation metric that we think is applicable for a lot of social science. Third, and finally, we show some promising results from a zero-shot entailment type model and identifying political events in text. And we think that there's a lot of room to go here in not using a zero-shot model, but providing some fine-tuning on top of that with some labeled data. So we encourage you to use our data set. We think it has a lot of applications beyond the ones that we've used here. So we think it will be a useful benchmarking and evaluation data set for a wide range of tasks, including zero-shot and few-shot document and sentence classification, ranking and retrieving models, using more information retrieval type models, and finally evaluating QA and event extraction models. So we hope you'll take a look at the data in full paper, and we hope that it's a useful resource for this community. And I think we can take questions now.
Thank you for the talk. It's very interesting. Mr. O'Connor, Brendan O'Connor.
Oh, I was just doing clapping. I have no questions.
Sorry. I see Ali has a question. It's the first in my list.
Yeah, thank you very much. Amazing work, a lot of stuff to just continue from. I'm mostly curious about the recall quantification. It has been an issue for us, and the only solution we could find is to get random samples from the whole archives. And we are not sure how much it works, because still it is an estimation. So when I first read the abstract of your of this paper, I understood it is like you annotate all sentences in March, published in March. But you mentioned in the talk you filtered based on place names. How much data is eliminated? Have you checked maybe 100 documents whether you are really covering or missing much? This detail would help me a lot.
Yeah, so we used after the keyword filtering, so we used the name of the state where the violence took place and the main city where the violence took place, and just those two included a third of the documents published in March in the whole Times of India. So we ended up, I think, discarding a lot less than I expected that we would. So this was it ended up being a third of the articles published by the Times of India, which was about 1,200 articles.
I see. Thank you very much.
Next is Ken Barker. Ken Barker.
Hi, Andy. Thanks for the talk. That was really interesting. I like the resource. So you said you used for the prompt for the NLI model in zero-shot, the prompt you used was the declarative form of the question you're interested in, right?
Mm-hmm.
So, I mean, these things are really notoriously sensitive to the prompt that's used. Did you try any other prompts or experimenting with tweaks on the prompt text?
So we experimented a little bit, and I can't remember if they ended up in the appendix or not. Yeah, this was something that I think Brendan was pushing us to include more of. But I think that there's certainly room to get more accuracy out of the MNLI Roberta model in a zero-shot way. But I think ultimately we wanted this to be a baseline that sort of gave a rough sense of how well that they worked just out of the box, and also sort of thinking about what a sort of matching the way that we set up the evaluation to what a social scientist would do. So using the keyword approach, and then also not really trying to tweak the prompts so that we could get as much accuracy as possible. So I would bet that you could get a few extra points by changing the prompt a little bit, but I think we really wanted these to be, zero shot, you set it, you apply it to the data and see how it does. But
yeah, I mentioned it because
I think for production, tweaking this would be pretty fruitful.
Yeah, I just mentioned because a lot of people have shown that it's not just a few points, that the choice can have really wildly different effects on the accuracy of it, from like 0 up to 90s. So
yeah, I can say a little bit. So we have qualitatively, we actually were surprised that certain wording variations we tried did not cause as large of a change as in line with those results. I don't know why. Maybe we weren't doing radically different wordings. I would say it's really important future work to evaluate this. And I think in NLP especially, we need to think more about the variance over the choice of prompt, more so than trying to generate hundreds of prompts to get good aggregate ensemble performance, because it's the low shot is what matters. So it's a great thing to investigate more.
Yeah. Cool, thanks.
I think we should go towards the next talk of Mr. Zhou, which is on trade event, corporate event detection for news-based event driven trading. So this seems to be an interesting talk on corporate events. We haven't had something like that in the program up to now. So please, Mr. Zhou, let's go on.
Thank you very much. Yours. Please let me share my screen first. Oh, sorry. Can you see my screen for now? Yeah,
we can see it. Okay.
Hello everyone. Yeah, thank you very much. Hello everyone. My name is Zhou. I'm a second-year PhD student in the Department of Computer Science at Northwestern University. And here it is my great pleasure to introduce our ACL findings paper here. And in this paper, we aim to analyze how news articles may influence the stock market. And we introduce an event-driven trading strategy that automatically detects corporate events from news articles and use that to make some trading decisions. So the main problem we're trying to solve here is news-based stock prediction. This is a very natural problem because, as we all know, that news articles can have big influence to the stock market, because some information contained in this news article may greatly influence investors' opinions or perceptions about different companies and about even the entire market. And this change of options may lead to some stock trading actions, so that the stock market may change dramatically when some news articles is published. And this is definitely a very open problem because different people may understand news articles in their own way. So some researchers have tried to use the sentiment of news articles as the indicator of the stock movement, and some of them may use the textual features, like directly take the news article as input and the stock rise or down as output to make some prediction. In this paper, we resort to corporate events. Comparing to sentiment and textual features, corporate events has two big advantages. First, they are objective facts. So unlike sentiment and textual features that may depend on the author and depends on the source that it is published, corporate events are objective facts. When it takes place, no matter how you describe it, it is there. And second, and most importantly, corporate events can have very significant and predictable influence to the stock market. Here, I prepared two examples to explain why this happens. So the first, one of the corporate event we investigate in our experiment is called guidance increase. Here, the guidance refers to a company's estimation of its future earning. For example, a company's estimation of its earning in the next year. because a company's market value highly depends on how much money it can earn right now and how much money it can earn in the future. So if a company is expected to earn more in the future, then it is very likely that its stock price will go up. And the second event we take as example is called stock repurchase, which refers to a company announced to use some cash to buy back or repurchase some of their outstanding shares. Because if our company's market value equals to number of outstanding shares plus price per share, and if a company's market value doesn't change much after this stock repurchase, then as the number of shares go down, the price per share will go up. So as you can see, some corporate events do influence the stock market with some very good reasons. And based on this insight, we propose an event-driven trading strategy like this. So this is a pipeline of our model. This is quite simple. This pipeline only consists of two components, an event detector and a trading strategy. And the only input here is news article. So for each news article, we first send it to an event detector to detect a corporate event, as well as the company that this article is mainly about. Then, if any corporate event is detected, we will this trading policy will make some trading decisions on the related stock, like the company that this article is mainly described. And this is the proposed event detector. So in this paper, we only detect event mention instead event trigger or event arguments, because what we really care about is whether some corporate event is described in this given article or not. So we formulate the event detection as a joint sequence labeling and sequence classification problem. So for each token of the article is first passed to a text encoder like BERT to get a representation. And this representation is then sent to a low-level detector to perform classification to determine whether this token describes a specific corporate event or not. Then all the low-level predictions and the article representation are combined together and sent to the high-level detector to detect whether this article describes some event or not from the article level. Then the high level and low level predictions are combined together at the final prediction. And to detect the company that this article is mainly about, we use a separate module called ticker recognizer, which is basically a text matching function that use very sophisticated rules to perform text matching between like company names and all the company names like listed in New York, NYSE and NASDAQ, and with this article to find the most relevant company that this article is mainly about. And after an event is detected, to see how it may impact the stock market, we use a very simple trading strategy, which basically get a buy or short selling trading signal singly based on the event type. Like every time a stock repurchase is detected, we will directly do a buy on the related stock. And every time a dividend card is detected, we will directly short selling the related stock at the time the news article is published. So this is basically the entire model. And to really train and evaluate our model on the real world data in a large scale, we collect a new data set called ADT, which consists of mainly two parts: corporate event detection and text-based stock prediction benchmark. So for event detection, we collect a lot of news articles and assign each token of each news article with the event type label. So for example, if this subsequence of this article describe the corporate event dividend increase, then all the token of this subsequence is labeled as dividend increase. And also Similarly, if this subsequence describe a corporate event called stock repurchase, then all the token within this subsequence is labeled as stock repurchase. And all the other tokens are labeled as other. And there are, in our data set, there are in total 11 event types and in total 9,800 news articles. And we choose these news articles based on some discussion with financial expert and based on our own finance knowledge, and also based on the news availability. So maybe there may be some other events do also have some big influence to the stock market, but the news of them may not be available, may not be easily available. So this is for the event detection. And when the event detector is trained and evaluate, we want to see how we can use the corporate event to analyze the stock movement, so that we collect another data set, which is for stock prediction benchmark, and specifically text-based stock prediction benchmark, in which it can includes more than 300,000 of news articles and with a time span of over 1 year. And more importantly, all of the news articles are acquired from either PR newswire or businessware. Both of them are very high quality and first-handed news sources. So which means almost no one in the world has seen the news before they are published on these two sources. So this is very important for our benchmark because this makes sure that the publish time of this news article can accurately account for the stock movement at that exactly time. So for each news, so after we have collected all the news articles, for each news article, we assign it with very detailed labels, including the adjusted minute level timestamp, as well as the automatically detected ticker, and very detailed price data of that ticker around the time the news article is published. So this allows us to directly evaluate our text-based stock prediction model directly on this data set. So even if we don't have access to very detailed like minute level historical price data, we can still use this data set to evaluate the stock prediction model in many different ways. So this is all about the database, and this is the result of our model on the EDT dataset. Here we use two trading strategies, one called TAE and one called TAB. Here the TAE refers to a trading strategy that buy the related stock at the moment that the news article is published and sell it after 1 day. And the TAB refers to a trading strategy that buy the related stock at the time the news is published and sell it on the highest price of that day. So this is impossible to achieve in real world, but this estimate like the maximum value that one can achieve with the detected corporate. And in our opinion, this single model which buy the stock and sell it for after 1 day, evaluate like the minimum value one may achieve with a detected corporate event. As you can see, even with the simplest trading strategy, the event-based model has achieved an average return of 1.7% in every transaction. And this is for day trade. So this is already a very impressive result, indicating that how effective corporate event is in indicating the stock movement. And if we can make trading perfectly, we can achieve an average return of 10% in every transaction and in day trade setting. So this shows how big or how significant the stock market may change due to some corporate event. And these do support our insight that the corporate event can greatly change the stock market. And here, I also prepare a small demo with our trained model to directly illustrate how our model works. So let me reshare my screen. So like, oh, please wait a minute. Oh. So we built a very simple tool on our GitHub report, and this tool can mainly do two things. One is analyze the news article and basically do some sentiment analysis and do event detection. So let's see, for any news article, what we only need to do is to provide its link. Then we just core this function. And so for any news article we want to analyze, we just provide its link. And this tool will automatically download it and parse it. And then it will analyze its sentiment and detect all the corporate events that are mentioned in this news article. And it will also highlight the subsequence that specifically describe these corporate events. Like we can see other example here. So hopefully this tool can help researchers in this direction to get some insight of why this news article may lead to some big movement on the stock market, and it may provide some it provides some visualization for the event detection. Based on the highlight part, you can directly see, you can directly check whether this model works correctly or not. And based on our own experience, the event detection is very accurate. And we also provide a single tool, a small tool to scrape the Reuters, like the Reuters website, to get all the historical news articles back to 2017. So to do this, we can use a very single command to download all the news articles for a specific company or for all the companies. So with a very single very short command line command. Let's say we want to download all the news articles for NEO. Then we just simply type it, and it will automatically open a Chrome browser to just go through the entire website and click and collect all the links that to the news articles that are related to NEO. And as you can see, 49 news articles are found for NEO, and we just singly call another function, and it will automatically download all the newses. So yeah, so it may take some time, but this is basically what the tools are for. And I think Reuters is a very good source for collecting news articles. So I think our interactive and analyze tool, and also the news downloading tool can be helpful for the community if for like researchers in many different ways. And this is basically all my presentation, and it is my great honor to present our work here. And I have uploaded all the aforementioned thing, including the code and the trained model, the data set, and the tool on my GitHub report. So please don't hesitate to use it. Please don't hesitate to reach out to me for any question or suggestions or discussion. And please let me know if you have any questions.
Thank you very much for this very, very, very interesting talk. I personally have questions, but let's see if someone else from the audience has questions for you. I see Mr. Hu.
Hi, thank you very much. This is indeed very interesting. So I wonder, have you kind of analyzed the event classification, as well as just what type of company does the model works well, and what type of event, like as you defined, whether it's a dividend increase and things like that? I assume there is a difference.
Oh, yeah, absolutely. In our paper, we have analyzed the influence of different event types, and it do shows that some of event may lead to an average stock change of over 10%, and some of events just lead to very slight event change. And perhaps I can directly show it. We have analyzed this in our paper, and as you can see, some of them leads to very high win rate, which means we can directly relate the event type to a stock rise or down, and some of them leads to very big like average change of the stock, and some of them leads to very small changes.
Cool. That's very interesting. Also, so you mentioned there is some research on using like sentiment classification on like the entire news article or something. Do you have like a baseline comparison with that kind of method?
Yeah. Sorry, I forgot to introduce that. Like in this table, the first 3 lines are sentiment-based models, and the last 3 lines are event-based models. So you can see there is a big difference between them in terms of the average return.
Do you think
so
this is
means, yeah, I think this is an indicator that stock price always often changes dramatically after some corporate events take place. So there is a larger average return with both trading strategy. So this means the stock price do change a lot. I mean, comparing to other indicators.
There is a question. There is a question from Osman Mutlu. So sorry, if you want, you can discuss later on the chat or meet on Skype for the discussion, because now we're running out of time. I'm awfully sorry. We're really running out of time. It's not possible to concentrate on only one question. There was a question from Mr. Mutlu.
Yeah, you mentioned I can write it on chat, so I was just writing it on chat. That's why. Can I ask the question?
Yeah, of course.
Okay. I was just wondering.
Please go on.
If you like experimented with confidence threshold, especially considering like your evaluation method is average return instead of something like accuracy, because you would value precision more, right?
Yep.
So did you experiment with confidence thresholds of your model?
Oh yeah, actually, in the real experiment, like we did include some confidence threshold, but that's like some empirical threshold. Like if the model has a confidence of like, let's say more than 80%, then I would think that it indeed find some corporate events. If the classification probability is relatively low, then I would discard that. Detected results. I mean, I will skip that news article for trading.
Okay, thank you for the talk.
Sure, thanks.
Thank you. I myself had one final question. Obviously, what you're doing is useful to detect the stock market going up and down, the stock market change, but in the stock market, particularly, I mean, especially in the stock market, when the stock exchange opens, all the news, usually most 90% of the news, they're published just before the opening of the stock market, when the prices and then the prices already changed. So the news monitoring for the stock market, my impression, it has a limited, more limited value than maybe other models which are based on patterns of raising and lowering of the stock value. Simply because the news are published most of the news are published just before the opening of the stock market, and then the prices are already adjusted. They change it when the market is open, and an investor cannot do anything. Because I have been experimenting with such systems, and my impression was that.
Yeah, this
that
is
the
a
news
very
monitoring
great
is limited.
point. Yeah, and based on our experience, like the news articles published before the market open and during the market hours do leads to different results. And we didn't show that in the paper, but I can discuss it a bit now. So for news articles that are published out of the market hours, which means people can see it like almost people can see it before the market opens, then it doesn't lead to much profit or average return. But if we only treat on the news articles that are published during the market hour, just at exactly the time that news is published, then it leads to very large average return. So I think this is like an advantage of the like a computer over human, because it can read the news articles very quickly and make trading decisions very quickly.
That's very interesting.
Very good point. Yeah.
Thank you for this observation. This is very interesting. Now we can go to the last, but not last as in importance, talk in our session, which is on the ethical limits of natural language processing on legal text. Ethical limits on natural language processing begin to have more and more importance in the era of Facebook and the Twitter, and with the spreading of the social media and all the scandals around those new media. The talk is going to be presented by Dimitrios Tsarapatsanis. So, Mr. Tsarapatsanis, please, you're here. The presenter of the next talk, Dimitrios Tsarapatsanis, is here, or we have to skip it?
I haven't seen or heard anything, so maybe we should just.
We can pass to the 10-minute break, maybe. And in any case, we're in time just for the break. We are behind in time. We're too late in any case.
Yeah. So in 15 minutes, a bit more than 15 minutes, 3:20, we will start.
We should start in 7:06.
Yeah,
3:20.
Yeah, the time changes for everybody. So let's just say in 15 minutes, guys.
Yeah, exactly.
And
10
we
minutes.
will talk about all of the shared task results. And we will, some papers will be a bit longer because they achieved somehow the best score for some evaluation scenario. There are 13 of them, by the way. And the remaining papers will have 3 minutes to tell us about their approach. So see you guys.
See you.
Thank you very much, Hristo. It was really amazing.
It was a pleasure.
Yeah. Hi, everybody. Do you hear me?
Yep.
Thanks, Salvatore. And I hope you see my first slide.
Yep.
Great. Thank you very much. So it is better if we start because we have many presentations, and I hope the time will be enough to allow the speakers tell about their approaches. I will try to keep it short with pointers mainly. So this is the workshop, Challenges and Applications of Automated Extraction of Socio-political Events from Text. We have the main track and the shared task track. Just to acknowledge, this is the fourth event. We started in 2019 with Clay and continued until now. Just to acknowledge my co-organizers from many institutions, a lot of help and direction, so we are here. And all overview is in this overview paper. The shared task has 3 tasks. One is the multilingual protest news detection. We have 4 languages. I will talk now about this one with 4 subtasks. And then Jakub Piskorski and Juan Zavarella will talk about the other tasks. Again, to acknowledge my contributors, Osman, Mutlu, Erdem, Y.rük, Farhana, Ferdousi, Liza, Ritesh, Kumar, Shyam, Ratan. So we could bring all this stuff together. For task 3, the order should be reversed, but anyway, the task 3 aims to identify, to understand whether we can replicate event maps that are officially published or crowdsourced. And it started with Salvatore's initiative and a lot of work around it by all these people. The task 2 again started with the initiative of Jakub Piskorski, and he worked with his team to make it possible, like fine-grained event classification in news-like text snippets. It focused on few-shot and zero-shot learning scenarios. I will focus on the task 1, multilingual protest news detection. 4 subtasks. It is a pipeline for annotation as well. First, we annotate documents, all news articles, like we see the whole article, not just a snippet. Then we split the sentences and annotate these sentences as well. And then we identify whether 2 sentences talk about the same event. And then from the event sentences, we extract events with their arguments. Just to be clear, protests are mainly known, the definition we use is known as contentious politics, and any form of grassroots political action and actions of political and non-governmental organizations that are aimed at mobilizing the public in the name of political demands and grievances. Can be almost anything, and the actor is important here. And the definition is based on the actor who do this thing. Therefore, it is a bit different than the pure verb semantic based definitions. It should, the time and the place should be clear, and feature plans or threats are not, doesn't count. The most important 2 aspects are, like Andrew has mentioned, like quantifying the recall and trying not to restrict ourselves. So we did a lot of experiments and work with random samples from whole archives. By whole archives, I mean last 20 years, because those we could access digitally. And the annotation quality. So a lot of care is taken there. I will refer to papers later if you are curious, or we can discuss somehow. So consistencies and double checks and adding additional annotation tasks just to limit the scope so annotators could focus on. They are all political science graduate students and trained on linguistic annotation and on the case country to understand its political environment. So the annotators could agree, hopefully. That is same. We have a couple of countries. For English, we collected data from India, China, and South Africa. And for Spanish, Argentina, and for Portuguese, Brazil. And for Hindi, our co-authors from India prepared the data on farmer events, farmer protest events, based on our own definition. We applied, first we annotated a couple of thousands random samples, but after that we moved to active learning and we measured its what we lose. So it is 3% of recall measured on a random sample. And the precision becomes 60%. That save us a lot of money. So the documented classification is just protest versus non-protest. Feature events doesn't count. Based on a country, there are many corner cases. But somehow we extended the annotation manual, or we agreed, or we have been working very closely with social and political scientists when we are not sure about the label. The sentence is similar, but it should have an event trigger or event about it. And then the event extraction, the event trigger, the event mention, maybe it is not the trigger, but referring to the event trigger. And many arguments. Those are the ones we are using here, and the most reliable ones based on our annotation. Because we read all of the news article, there are articles that contain multiple events. So it was a challenge to separate events. We have a lot of manuals, and we have some reasoning or experiments why we choose this line. I will not go into detail, but we need internotator agreements. Here it is Crepandor's alpha. The time, the trigger are the best, and then the place, facility, or participant are less reliable. But this is the first batch of when a pair of annotators work on a set of documents. But these annotations are corrected, double-checked, and with spot checks or semi-supervised approaches. So therefore, we just use these numbers to see whether our annotation manual is okay, and whether the annotation quality or the task is hard. So we have, like, this is, we think, in this field of event information collection or protest information collection, we haven't seen any study until maybe last couple of years, 1 or 2 or 3 years. So just title and lead-in sentences were being used, but we weren't sure whether this is enough. So therefore, we kept reading all articles. And now we have numbers on how many events, how many articles contain one event, one single event. It is more than a half, it is 59%, but the remaining 40% contain more than one event. So we can't assume extracting one event from title or leading sentences. We can't consider it as enough, although it requires a bit more investigation. Maybe the 40% is just repetition and may not be useful, but still, from an extraction point of view, we should be aware of this fact. For each event is represented like only 35% of the time with only one single trigger. And many events, like 65%, to be able to collect its information, you should assume there is one more event mentioned about it, and maybe sometimes 2, sometimes 3. So you need to identify the sentences that has information about these events. And the tokens are like, they are mostly one single token. Some very rarely more than one token. Finally, the data for this particular shared task, we have JSON files for the news articles for subtask 1 and 2, document and sentence classification. We have the text and the label, and we have an ID for reference. For document level, we could share only 1/3 of the article text due to copyright reasons. So therefore, the numbers, scores can't get above a certain number, maybe not above 90, because the event information is in the part we cut. For subtask 3, we give the sentences as text, and we give their numbers. These numbers can be anything else, but we just use them as they occur in the article, and their grouping, whether they are about the same event. So here, the sentences 5, 7, and 8, these are in the same order, about the same event, and the first sentence is about a very different event. The event extraction data is the traditional data with BIO schema, and this is in 2 formats, like the same data, with just for illustrative purposes. So how many of the events are presented with more than one sentence? In languages, it is here, like more or less, you can say comparable. More than half of them. If the assumption of using one sentence to extract an event and not going to the second sentence works a bit more than half of the cases. But in the remaining cases, you should go and find the information from other sentences. And those are the numbers for the triggers and argument types per language. We don't have Hindi here because we have Hindi data only for document level. Here are the numbers for the train and test. We shared the train and nobody has seen the test data. We evaluated it on a Codelab page. So finally, the results. I will just mention the pattern, and we leave the floor to the participants. Like for the document classification, the first one is 84, and the second one is very close to it. So for Hindi, we find it surprising without any Hindi training data, with only using data in English, Portuguese, and Spanish. Some participants combine this data. You can do quite well. So just remember, the top performance could be maybe around 90%. For Portuguese, 84. The second one is 82. Sometimes teams have some gaps between the first and the second. And for Spanish, it is 77. And the second one, just look for points. So for sentence classification, there is a similar pattern without Hindi here. For sentence co-reference identification, this is the task of finding sentences that talk about the same event. We have pretty good numbers, although they are close to each other here. Again, there is gaps, some less than others. Here for event extraction, the first team really have a large difference with others, and it just showed us the better, the more you work, the better scores you get. So, and this is a sign for all of us, like it is hard to say, okay, without these numbers, we would assume the state of the art should be around 73, maybe if you push for it, 75, but who knows? It is already 78. So as a summary, multilingual and cross-lingual approaches work. It is surprising how we see numbers another thing, for Spanish and Portuguese, we have limited data. So even with limited data using English and cross-lingual models, it works. Some teams merged training data from all other languages and used external data, so they could obtain best results. I talked about Hindi. Monolingual models outperforms multilingual models almost only when there is data. In all other cases, cross-lingual models are better. But sometimes, not sometimes, but English or monolingual models are in the first three, like almost always. We can say they have comparable results. And if you have data, use the monolingual models, it is better. That is it. So please let us know if you would like to suggest anything or work together for anything in this line. We are just growing and very happy to see all these interesting work together. We have a couple of tasks in mind, like demand recognition, violent event detection, ideology classification, or creating a global database of protest events. And most importantly, increasing number of the languages we are handling. We see what we will be able to achieve. The details are in this overview paper from this workshop. The corpus in this one, cross-context news corpus for protest, blah, blah. And the random sampling approach is detailed in this paper. And we just saw like the most important result. If you want generalizability, cross-context generalizability, don't use keywords, just use a random sample, and deep learning models or transformers take care of the rest. Thank you very much. Please let me know if there is anything you would like to talk or comment, whatever. We will keep the website up to date. The shared task details are here. And we have an email group that is activated from time to time to organize these events. Thank you very much for your time. And I am quite happy to finish in exactly 15 minutes. I can have one or two questions if you really have something to comment or ask, or we can just continue with the best papers, best scoring teams papers. Questions? Okay, we may have time later or in the chat. No, we don't have here in the chat. So we will continue with the paper of IBM. They scored quite well in many evaluation scenarios, in at least half of them. And they were in the second place in the remaining. So who is here?
Hi, I'm Jenny from IBM Research AI.
Welcome. Please.
Can you see my screen?
Yeah, we see it.
Hi, everyone. Today I will present our work on the case here. Task 1, multi-granular and multilingual event detection on protest news. This is a joint work with Peru, Ken, and Radu. So as you know, this workshop addresses the challenges and applications of automated extraction of socio-political events from text. And it's a workshop at ACL 2021. And we would like to thank the organization community for organizing the shared tasks. Our team, IBM MLPIE, participated in the first two shared tasks. In this talk, I will focus on shared task 1, multilingual protest news detection. Shell task 1 has 4 subtasks: document classification, sentence classification, event sentence coreference identification, and event extraction. There are 2 important features of these subtasks. First, these tasks are multi-granular, which addresses even the information detection at different granularity levels, from the document level event detection to the token level event extraction. Second, these tasks are multilingual, which include English, Spanish, Portuguese, and Hindi. So here are the data provided by the organizer. As we can see from the table, the size of different languages are different. The size of the Spanish and the Portuguese are significantly much less than English, while there is no annotated data for Hindi, which is a zero-shot task. The second observation, there are no official splits of the train and development. So we create our own. We randomly sample for most of the language and the subtask. We randomly sample either 90% or 80% of data as the training and keep the remaining at the development. But for subtasks 3 and 4, since there are very few annotated data, we keep them all for development. So subtask 1, document classification, tries to detect protest events at the document level. So we formulated this we use the transformer-based text classification model to address this problem. And since nowadays there are huge amounts of news articles in the world, so this component can be used as a first component of even the information extraction pipeline to extract relevant documents from with certain type of events types that we are interested in. So here is the architecture of our model. The problem can be formulated as a binary text classification problem, where we assign label 1 to article if it includes 1 or more protest news and 0 otherwise. Recently, studies have shown that large, deep transformer-based language models, when pre-trained on a large corpus, can achieve state-of-the-art performance with many NLP tasks. So, and also, since this is multilingual, we use the pre-trained multilingual transformer-based model, XML Robata, as the input text encoder. So the input sequence are mapped to subword embeddings. These embeddings are parsed to multiple layers of transformer layers. And we use the final hidden state. This is standard in the text classification models. We use the final hidden state of the sequence start token as a summary representation of the whole document and pass it to a softmax classification layer. So we try 2 different fine-tune strategies. The first one is to build a language-specific monolingual model, where we fine-tune a separate model with data from 1 language at a time. The second one is to fine-tune a joint multilingual model with data from all 3 languages. The performance of the models are shown in this table. So there are several observations. The first one is that we can see that a model trained for 1 language can achieve very good performance on other zero-shot performance on other language. For example, the model trained with English-only data achieve better performance than the on Spanish, than the supervised Spanish model. Another observation is that when we add in more data to the Spanish and Portuguese to the model, the joint model multilingual model improves on both Spanish and Portuguese. Here is the performance of the models on the final evaluation test data, and we prepared 3 systems. The first system is an ensemble of the language-specific monolingual models. The second one is an ensemble of the multilingual models, and the last one is an ensemble of both monolingual and multilingual models. So it's interesting that on this test data, the monolingual language-specific monolingual model achieved the best score across all 3 languages. Now let's go to subtask 2, sentence classification. So this is the event detection at the sentence level. So the model is similar as a document classification model, with the difference is that for sentence classification, we use a smaller maximum sequence length, where we use 128 for sentence classification. But for document classification, since the documents are much longer, we use the maximum of, for XML, but is 512 as the maximum sequence length. And also we try to fine-tune strategies. One is the monolingual model, the other is multilingual model. And here for the final grain, the sentence classification model, the observation is slightly different. Now the multilingual model, when trained with all the data, perform better than the monolingual model on the low risk of Spanish and the Portuguese language. And later we will see that for the final grain, the token level even extraction, we have similar observations. The subtask 3 is even the sentence reference identification. So this task is trying to class the sentences to find a sentence that refer to the same event. And our model is to have two components. One is the peer classification modular, the other is a grammarative classification modular. So for the peer classification modular, the inputs are the even sentence pairs. We also use a pre-trained class transformer XML robota to encode these sentences, and we classify whether these sentences belong to the same class, belong to the same events or not. And also the scores returned by the model is input for the next modular, a grammarative classifying modular. So in this classifying modular, it starts with one class for each sentence, and then during each iteration, the classes are merged based on the average inter-cluster link similarity scores. And that procedure will stop when the average link similarity score is below a threshold. So for the peer classification input, we tried different variations. The first variation is just use the even sentence pairs. The second one is the even sentence pairs with the triggers marked. So we mark triggers in the sentences. The next one, we further mark the arguments, the place and the time arguments. And while the fourth one is we use the ACLED trick types as a feature. While the first four are all trained with English because there are not much data for Spanish and Portuguese. The last one, we try to build a more monolingual model on translations. We translate the English to Portuguese and the Spanish and train a joint model. The performance on the data set are here. So the variation 1 achieved best performance on Spanish, while the variation 3 achieved best performance on English and Portuguese. Here are the model, the performance on the final evaluation test data. So here it's very surprising that the English only model, the variation R1 is trained with English only, achieve the best performance, and it's quite good. So which means for this task, when we're trying to find whether the two things refer to the same thing, the co-reference task, the zero-shot approach turns out to be very good. So the final subtask is event extraction. Here is the final grain level, is token level. We're trying to identify the triggers, also the arguments like the organizer, the participant, the facility time, and the target of a model. We use the transformer-based sequence labeling model, and we explored several model architectures. The first one is a standard sequence labeling model where the input sentence sequence is mapped to support embeddings, and these embeddings are we directly classify the final hidden states of the embeddings. The second variation is to add additional dense layer with 10 activation functional dropout to make it a little bit deeper. The third one is we add additional CIF layer to model the dependence of the labels, which shows to be quite efficient for sequence labeling problem like name entity recognition. And we also try different data variations. So for the first three, they are English, and the fourth one are the same model actually with model 2, but we trained all the data together. And the last one is an example of the different models by voting between the system outputs. So on the left, we show the performance on the development data, and the right, we show performance on the final evaluation test data. So here, we also observe that the multilingual model, when the model trained with all the data together, achieved better performance, on English, on Spanish and Portuguese with our low resource data. So this is consistent with our observation for the sentence level classification, but different from document level. So we would conjecture, or we guess that maybe for final grained models, final grained tasks, aggregating data from different language is beneficial, while for coarse grained document level, aggregating may hurt the performance. So here are the final results of our models, and in the table we show the best score of our best system, and also the top score of all the participants and our ranking. And we can see that our models perform consistently well across all the language and subtask peers. Out of 13 subtask language peers, our models achieved the first place in 9 of them, and the second place of 4 of them. This also shows the robustness of our approach. That's it. Thank you very much. And now I would be happy to answer your questions.
Thank you very much, Zhihan. We don't have time for questions, unfortunately. Great summary, a lot of work. So I suggest
thank you.
Writing questions on the chat.
Yeah. If you have any questions, can send to us and Peru, and Ken is also here. We can answer your questions.
I have my own questions as well, but I will reserve them for later.
Okay.
Thank you very much.
Thank you. Thank you.
So we have DAAI. I guess Hansi will be presenting it.
Yeah, hi. I'll share my screen.
Please.
Okay, can you see my screen?
Yeah, please focus on the approach so we can make best use of the time.
Okay. Hello, everyone. Initially, I would like to thank organizers for organizing this workshop. In this presentation, I'm going to present our approach for task 1 on behalf of the team Day2. In this paper, in this paper, we describe our approach for event detection at document and cross-sentence level using the capabilities of state-of-the-art transformers. I will skip the task details, but among the subtasks, we joined with the subtask 1, document classification, and subtask 3, event sentence for reference identification. In these slides, I put more details about subtasks, but I will skip them. Regarding the methodology, I will start with our approach for document classification. We considered document classification as a sequence classification problem, and we used a transformer-based text classification architecture. So in this figure, I showed the architecture. As the input, we insert a sequence of tokens. In this scenario, the sequence is a document. And at the beginning, we add a special token named CLS to the sequence. Then from the output layer, we take the embedding of the CLS token, pass it through a softmax layer to predict the class labels. While selecting the transformer models, we specifically focused on improved versions for long documents such as long former and big bird. For event sentence co-reference identifications, we considered it as a sentence clustering problem. That means our approach mainly has two steps. First one is generating sentence embeddings, and the second one is clustering those embeddings. To generate sentence embeddings, we used Siamese sentence transformer architecture, which is shown in this diagram. For that, as the input, we have to insert sentence pairs. Then we generate their embeddings and then calculate the cosine similarity so that we can compare this similarity value with goal labels to fine-tune this architecture. That means to train a sentence transformer, we need sentence pairs and corresponding similarity labels. For that, we have to format given data. For each data instance, we generated all possible sentence pairs and then assign the label of 1 if both sentences belong to the same cluster and 0 otherwise. As the clustering algorithms, we used available algorithms, hierarchical agglomerative clustering and pairwise prediction-based clustering. We experimented different learning configurations like pre-trained, fine-tuning, from scratch learning, and language modeling. Also, we involved data-oriented learning configurations as well, like monolingual learning, multilingual learning, and zero-shot learning. This slide summarizes the transformer models we used for our experiments. Above table, it summarizes general transformers. Below table summarizes sentence transformers. To conduct the initial experiments, we separated a validation set from the given training data. This table summarizes document classification results for English language. We analyzed the performance of different transformer models with varying sequence length. According to the results, for BERT model, we can improve the results with higher sequence length, but for other two models, Big Bird and Long Former, we noticed that we are getting high F1 with low sequence length. This table summarizes the results for multilingual experiments. For English language, which we can consider as a high resource language, we obtained lower F1 than the monolingual scenario, which I explained in the previous slide. For other two languages, multilingual learning performed better than monolingual scenarios. This table summarizes the results for test data. For English language, our approach with Big Bird model become the winning solution. For other three languages, multilingual learning performed best with XLMR model. Results of event sentence co-reference identification. For English language, we experimented different learning configurations. Among them, sentence transformers built from scratch performed better than fine-tuned and pre-trained models. We involved language modeling as well, but it did not improve the results, and it is possible when we don't have enough data for modeling. To conduct multilingual experiments also, we used English data due to limitations in other data sets. Similar to English monolingual scenario, in this case also from scratch models perform better than both pre-trained and fine-tuned models. This table summarizes the results for test data. Among sentence transformers, both fine-tuned and from scratch models perform better than pre-trained models. Considering clustering algorithms for overall hierarchical agglomerative clustering perform better than pairwise prediction-based clustering. As conclusions, we can mention that state-of-the-art transformer models can be successfully utilized for socio-political event detection at the document and sentence level. The model performance can be further improved by involving proper learning strategies, and the multilingual capabilities of transformer models allow the approach to be extended effectively for multiple languages with low or no training resources. So that's all. For more details, I would like to recommend to refer to our paper. But if you have any questions, I'm happy to answer.
Thanks a lot, Hansi. Again, we should just skip to the next one. I hope we will have at and some time.
Okay.
We have the following talk is from Vivek Kalyan. In the title, there isn't the team name. I don't remember it by heart. Handshakes.
Yeah.
Welcome, Vivek. Please.
Hi, can you see my screen?
Yeah.
All right. Yeah. Thanks for having me. I'm Vivek. I'm presenting joint work by me, Paul Tan, Sean Tan, Martin Andrews. Yeah. So we are a group of researchers from Handshakes, which is a technology company from Singapore. We build our own in-house NLP systems from document classification, NER, NEL, recommendation systems, and so on. So some of our partners are Singapore Press Holdings, Nikkei, Financial Times, and they use our system primarily to add value to the news that they already provide. So this can be like document classification or extracting information from these news articles, be it like organizations or people that are in these articles. So our interest in this workshop is primarily because most of our current focus is mainly on English document, but there has been strong like commercial demand for expanding our capabilities to other languages. And so we are very thankful for this workshop and the organizers for giving us this chance for presenting our work. So I'll briefly go through some of the approaches that we have. So for subtasks 1 and 2 is article classification and sentence classification. So due to some like unforeseen circumstances, we were not able to use our experiments for subtask 1. And eventually what we did was use our experiments for subtask 2 to kind of inform like a baseline model. So you can see that the subtask 1 model is a much smaller model. So one thing that we try to ensure is that for each subtask to use a single multilingual model for all the languages. This is more due to how at the end of this workshop, how can we bring the models that we have and productionize it on our side. So for subtask 1, what we had is a linear classifier with multilingual LA-based embeddings, which were, so only the linear classifier is trained on the subtask 1 data. For subtask 2 itself, we have an XLM Roberta with a linear classifier head, and we train it on both subtask 1 and subtask 2 data, basically treating subtask 1 articles as an entire sentence. We found that this actually helped improve the performance. For all the data, we use the 80-20 training and validation split for this subtask. For subtask 3, which is a event co-reference identification, we use the multilingual BERT that is trained as a sentence pair co-reference classifier. So this is basically a binary classifier which takes two sentences and determines whether these are co-referential or not. Due to the low amounts of training data for the Spanish and Portuguese data, we translated some of the English data into Spanish and Portuguese using Google Translate. And during inference time, what we did is to predict if the sentence pair refers to the same event. And using this output, we basically did a greedy clustering of these co-referential sentences. So for subtask 4, which is event extraction, we basically modeled it as a NER problem. So using a XLM Roberta with a token classification head. For this subtask in particular, what we tried to do was to kind of split up the data into a primary language and secondary languages. So in this case, English would be the primary language and the secondary languages would be Spanish and Portuguese. And our goal is to basically train a model using only primary language and test it on the secondary languages. And to achieve that, we use word-to-word translations as previously done by Lepel et al. To basically convert the primary language training data into secondary languages. On the right, you can see an example of a sentence, KSRTC buses were attacked at 10 paces. And the two columns on the right are the respective translations of them. So you can see it works pretty okay, but at the same time, it also makes some mistakes of wrongly translating KSRTC into other words that are present in that language. But we found that actually we found quite a significant improvement using these translations than without. And just as a final step to kind of ensure the consistency of the predictions, we use Bit2B encoding to have some consistency with the BIO tagging. So some conclusions is that we were quite pleased that we could use a single model for each subtask, and it achieved relatively good performance compared to a single monolingual model for each language. And this is kind of promising because it allows for relatively easy and cheap deployment. And for subtask 3, we found that translation API gave us reasonable performance. And for subtask 4, this word-wise translation allowed the NER task to be transferred with quite good performance. That's it for me. Thank you. If there's any questions, I'm not sure if there's time for questions.
In the chat for now. Sorry, guys. And Hansi already answered the question, and I encourage you to interact there. At the end, I hope we will have time. We can chat as long as we wish. But for now, just to keep the schedule there. This presentation shows like many teams, each team shed light on different aspects of the approaches of the data, of the state of the art. So therefore, I really happy about it. Thank you very much, Y.rük. So the team No Conflict is the following one, Tian Cheng Hu and Nikolaos.
Can you see my screen?
Yeah.
Okay. All right. Hi, everyone. So my name is Tian Cheng Hu. Today, I'll be presenting our submission from Team No Conflict to case 2021 task 1. Our title is Pre-Training for Sentence Level Protest Event Detection. This is a joint work with Nikolaos, and we're from ETH Zurich. So I'll skip this part as time constraint. So basically, we divided the data set similar to what other people did. We focus on event sentence classification, and we only focus on the English model, but our approach can be extended to any multilingual model that you may prefer to use. And we divide the data ourselves, 80% for training and 20% for validation, because no official split is provided. So here's the approach. So it has been widely known to this community that large language models are very, very successful in a variety of downstream tasks. This is a typical pipeline. You take your favorite pre-trained large language model, and then you fine-tune it on a downstream task. And it typically works very well. Now, our approach is slightly different. We add a second pre-training step. So what it is still similar to a pre-training step with the same kind of mass language model objective, but we pre-train it on a relatively domain-specific type of text. So instead of training it on, say, Google Books, we actually train it on some sort of news article. Then the intuition is that large language models that are trained on this specific type of text might be more optimal for the specific downstream task we're focusing on, rather than like a model trained on a general text. So this is inspired by Gurengan et al. 2020, and also similar work was presented yesterday in this workshop. So we take Roberta, in our case, as the base model, and then we do the second pre-training, and then we fine-tune it on the downstream task. So the data set for second pre-training, there are a few considerations. So first, ideally, we want to use the exact same source of data as the shared task. So that means data from the Indian Express, New Indian, the Hindu, and so on. These news outlets. But unfortunately, it's very time and resource consuming to collect the data ourselves, and no existing data set covers articles from these outlets. So instead, we turn to the Palooza data set. This is a very interesting data set. It contains 0.9 million English language online news, political news articles. This is actually very important that it's only political news, not all kinds of news. It's from between January 2017 and August 2019. It has a number of outlets that reflect an average US news consumer ideology. So some outlets that are left and right, and some others that are more centered. So the result we achieve on our validation set, F1 score of 0.8395. On the testing set, it's slightly lower. We are the best performing submission in subtask 2, task 1, subtask 2 in the English version. And because our model only focused on the English version, we also want to just try our hands and see how this works on other language. So we just use simple translation tools to translate the test data. So it's basically a zero-shot setting, kind of. And we actually achieved the second best F1 score in Portuguese. So here are some analysis of the failure cases. So here, P means the predicted label and the L means the actual label. So the first class of error is basically the model just simply misunderstood the sentence. So the first example here is Bernie Sanders holding a political rally. I guess the model sees the word rally, and then probably because of statistics, it somehow thinks this is a protest event, even though it's not. And the second one is rule error. So this happens when the sentence could have been seen as a protest event in common sense, but it's not considered one according to the annotation manual. So here, the sentence, a protest is called for, but there's no definitive evidence whether it actually happens. So according to the label, it should be 0, but I guess the model hasn't seen enough of this, so it get this wrong. The next case is uncertain reference. So the event that a sentence is referring to is ambiguous. So here we have the act, and this in these kind of scenarios, I mean, even a human probably just cannot tell what kind of thing actually happened. So it's not very reasonable to expect the model to get these two correct. So, and the next case is indirect mention. So there seems to be some label inconsistency when an event is indirectly mentioned. Maybe the organizer can share more insight on this, but these two sentences, perhaps they should, at least they should have the same label. So the first one actually, let me see. Oh, so the first one, it's labeled 0, and the second one is labeled 1, but at least we're not sure if they should be labeled differently. Here's an interesting part. So we want to test the effect of named entities in this data set and this specific task. So what we did is the following. In one setting, we removed named entities in all the training and validation data. And in another setting, we only considered named entities in the training and validation data. So we remove everything else, even if the sentence has very few words left. To compare, we also have a random baseline where we draw labels from the ground truth label distribution in the training set. And because this is random, so to make it more comparable, we draw this random assignment from 100 runs. So a few things we can see here. First of all is that when we do not consider any named entities, so this is if we compare it to when we include all the named entities, the performance dropped slightly. So, and the next case is when we only consider the named entities, we still get, you know, some performance that's quite a lot better than the random baseline. So what this tells us is the model is able to rely on, you know, some statistics about the named entities in the data set to make judgments about the task, in addition to relying on linguistic clues. And also another thing that's worth pointing out is in all the settings, whenever we use second pre-training, it always performs better compared to the baseline model Roberta without second pre-training. Yeah, so that's all I have. And we did a few other things, and that's included in the paper. So feel free to read it and then reach out if you have any questions. I'll be happy to answer. Thank you.
Thanks a lot, Tian Cheng. A lot of work again, highly appreciated. So we should just continue with Francesco Re, if I
Yes, that's correct. Hello.
recognize him correctly in the group of the people here.
Yeah. Yeah. So hello, everyone. My name is Francesco, and together with Daniel, Dennis, and Nikolaos, we worked on the shared task, especially on the subtask 1. And we worked on subtask 1.1, so document classification, and on subtask 1.2, that is sentence classification. And our approach eventually was successful, specifically for the Hindi section, where we appeared first on the leaderboard. So here's a little insight on how we proceeded. We focused mainly on two things. Firstly, we focused on the data set, as the data set that was provided by the shared tasker presented a strong imbalance ratio on one hand, as of the classes, as usually conflictual articles or articles related to protests were way less than articles not related to protests. And what's more, in many languages, such as Portuguese and Spanish, didn't have as many articles as, for example, the English language. And for some, for the Hindi language in the subtask 1.1, we of course had to provide predictions for it, but we didn't have a training set. For this reason, we decided to extend the data set, and we did it by getting some additional sources. For the conflict-related articles, we used the ACLAD dataset, which is a dataset that consists of very short text that, despite tend to follow a similar pattern, still turn out to be useful for the final predictions. And we also use the Europe Media Monitor dataset, which also allows that also has data in Spanish and Portuguese, as the ACLAD dataset only had English documents. We also added additional sources for non-conflict related events, and specifically we scraped online magazines that we thought would be blatantly non-conflictual. So for example, anything related to fashion, sport, or art. And once that we gathered all these additional data, we merged them into several new data sets. Like we merged this new data and the old data, like the original data, into different new data sets. Each of them had different specifics, but the data set eventually that turned out to to the best predictions had this following specifics. Specifically, we kept the same class imbalance ratio that we had on the original dataset. And we did that by scaling up the dataset and adding non-conflictual articles and conflictual articles so that the ratio would stay the same. And we did that because we thought that we would also kind of incur in a similar imbalance ratio in the test set on the evaluation phase. And another thing that we did on this data set was to basically take all the articles that we had and translate them into every other language that we had to we were supposed to predict for. So eventually we had a corpus of articles where for each language had all the articles all the overall articles. So this eventually, I think, was also one thing that could benefit the good performance on the Hindi language, because the Hindi language eventually had all the articles that were presented in the other language but translated into Hindi. And for the model, we use a multilingual model, XLMR model. And I think the interesting observation is that maybe in a multilingual model, we still give as input all the information in different language, but still somehow the fact that we priorly translated everything into different languages and then input everything is still, like, the fact that it improved the performance, I would say it can be interesting. And so, of course, here are the more specifics of the models that can be also found on the paper, and all the experiments and the results that we did eventually. Also, these it can be better and like seen on the paper as maybe for time constraints. Yes. Also, we had a good discussion session that you can feel free to go and look it up. But yes, I think that for the prediction, for what it regards the prediction task, especially on Hindi, that's all. Thank you.
Thanks a lot, Francesco. Quite a lot of work, and it really shows how it works in a zero. How should we work in a zero-shot setting? We now have Nus IDS, Fiona, and Think Tan. I hope I pronounced all this stuff close enough correctly.
Yep. Okay, so hi everyone, can see my screen, right?
Yeah, we see it.
So I'm very happy to be here today. I'm representing my team at the National University of Singapore Institute of Data Science to present our work on Chat Task 1, Subtask 3 of the case workshop. So just briefly, the task we worked on was just the Event Sentence Co-reference Identification task, or ESCI for short. And the best models that we have achieved first, second, and second for Portuguese, English, and Spanish test sets during the competition respectively. So the task at hand aims to cluster sentences that refer to just the same event in a document together. So for example here, a document of 3 sentences that has the first and third sentence referring to the same protest that affects the highway are clustered together, whereas the second sentence refers to a separate protest. So yeah, so this was the task. And additionally, this year's competition also included multilingual corpora, namely Portuguese and Spanish texts. But as mentioned by many, notice the data sizes for the non-English sets are very small. So our approach is to first convert sentences into binary pairs and then score each pair based on whether they are co-referent or not. Subsequently, we then take these predicted probabilities and send them through a clustering algorithm to obtain the document level sentence clusters. So just focusing on the first section of our pipeline, our sentence pair representations are constructed from fine-tuned bird embeddings. And then subsequently we append the pause embeddings fed through and feed them through a bi-LSTM model. And then we also combine linguistic-based lexical and semantic similarities that we score between the sentence pairs. So specifically, we categorize them into two portions. The first portion, we call them basic similarities, whereby we simply use the counts or Jacquard overlap of verb, nouns, and entities occurring in each sentence pair. For the extended similarities, we use cosine similarity of normalized dot products of vectors, corresponding again to parts of speech or name entity text. And then we also take the average word vectors using glove representations. Another thing we explored was to use this simple approximate bigram kernel proposed by Ozates, which basically incorporates dependency relation similarities. So actually we detail more information of these features that we curate in our paper and the source code that we uploaded. So for clustering, we actually used the last year's best performing team's proposal by Ors. In his paper, he refers it to under algorithm 2. And so you can refer to the code for more information. But just to note, we also did experiment on community detection, graph clustering algorithm, and regular hierarchical clustering with single linkage. But we noticed that these all perform worse than what Ors proposed. And so that's why we started that. Nevertheless, we did do a minor tweak. If you notice in his paper, he actually used the 1-0 co-reference statuses and feed them through clustering. But instead of that, we actually feed the predicted probabilities because we believe that they serve as good tiebreakers instead in his paper, whenever it ties, they actually just give the lower indices the priority. So in general, our contribution is really exploring the features that we add in terms of parts of speech and curated similarities. So we show that in the cross-validation set, adding all our additional features improve the scores beyond the baseline BERT model. And this model achieved 84.92% during our cross-validation. And again, 81.2% F1 score on the unseen test set. And this ranked second amongst the competitors during this shared task. So noting that we combine all the languages to create our train set. So that is, the train set is actually predominantly comprised of English text. We also noticed that it is unsurprising the fluctuations in performance on the validation splits largely tally with the fluctuations in performance on the English competition test set. So because the competition also worked on multilingual settings that are resource poor, we had to create a model that could concurrently work across languages. We hope to transfer some of the learned patterns from the data-rich English corpus to the other languages. And so we use two methods. The first is just simply to translate all these multilingual text to English and then use English BERT directly. Whereas the second is to use multilingual BERT directly on this multilingual text. What we notice is, as summarized by many people also, that the multilingual model works better for the multilingual text. And this model that we have, which includes all features except for the extended similarities, performed the best for Portuguese during the competition, achieving 93.03% F1 score, and second for Spanish, achieving 83.15% score. We also believe that most of our findings and conclusions regarding the non-English settings will need more work and more data to have more robust conclusions. So here are some cherry-picked examples to demonstrate qualitatively how our model is performing. These are the examples where, for the English model, we actually predict correctly. But I think more interestingly, we look at the examples where our model predicts wrongly. So here, the binary predictions show that sentences 1 and 2 are strongly related to one another, and hence it was clustered together. We do not have a clear understanding of what is focusing on because we didn't actually study the attentions. However, we do note that it's interesting that terms like my and wife that occurs in sentence 3 and also in sentence 1 and 2 are not focused on. So it seems that there's no memorizing of surface terms in this example here. And in general, during our experiments, we found that using probability instead of the 1-0 predictions helped resolve many ties during the clustering step. But over here, we find a corner case where using the probability in ORS clustering actually harms our outcome. So in fact, this example would have been correctly clustered if we stuck to the 1-0 predictions. So this is what we actually predicted. So if you focus on the binary coefficient probabilities at the top right corner of this slide, the descending order made it such that the sentences with ID 13 and 29 were separated into a cluster alone. Here we highlighted in purple. So you could say that this ordering is one part luck, but it's also possibly one part reflecting the nuances that might have been picked up. Specifically, we noticed that maybe terms like resolving or managing a strike are more related to one another than rest of the orange sentences, even though they all actually refer to the same strike. And so maybe this is then looked at first. So that's all for our sharing. If you have any questions, I will be happy to take them.
Thanks a lot, Fiona Tan. We have time now. We have at least 5-6 minutes until the break, and we have the break 10 minutes. So for this one or for other questions, just raise a hand. Okay, I don't see. So sorry, it is a bit fast, but at least these presentations really show how a lot of work and different aspects are worked on. And I hope this will trigger interest to go to the actual papers and maybe continue with the following steps. By the way, co-author of the ORS et al., Reyhan Yenitarzi should be around, and there can be additional contacts about following up this work. The only thing from me, one comment, Fiona, when you say we would need more data and more work to make it more robust, I agree, more work is always good, but let's try in this era to be less data hungry. This is for all of us.
It's definitely better to have more, but I was referring more of like, we couldn't make a lot of conclusions on the multilingual settings. We couldn't say that, oh, this model definitely works better for Portuguese text, because it was just based on what we observed so far. But I don't dare to make the extra statement that it will work all the time. Yeah.
When we prepared the data, it was like a trade-off. Should we provide more training data or more test data? So, and to be able to get reliable scores, reliable measurements, we tried to have more test data.
I actually have a question. I don't know, but I feel that since the scores differ so much in cross-validation and test set, is there some difference in the way you all select the data somehow that led to this difference?
The splits, maybe the data is randomly sampled, so it has a variety, and between and the sample sizes are too small to represent the whole 20 years, like millions of news articles. So therefore, my first idea or comment would be, because the space covered is wide, it is not that surprising to have these models with these training settings to have different results. If these were collected with keywords or a bit more restricted time period, maybe it could be more focused or similar results. So yeah, we have some comments about the other paper. Okay, then I don't see anything else. Let's continue in 10 minutes. Nikolaos will present the overview of task 2. To be honest, I find this task a bit more interesting because like models really should be very capable to be able to tackle these tasks in few shot and zero shot settings. Well, looking forward to see as many as possible of you there as well, and see you. Hi, everybody. Do you hear me?
Yes.
Perfect. Jakub, are you there? Jakub Piskorski.
Yes, I'm there. Nikolaos Stefanovic will give an overview of the shared task.
I know you are on charge of this task, so you are chairing this session if your settings are okay for you. Because there are additional insights from your participants as well. And I think it is a perfect thing if you do it. Thank you. So the floor is yours, Jakub and Nikolaos.
Okay, Jakub, shall I go without further ado?
Yes.
Fine. Okay, can you see my screen?
Yeah, we see it.
Okay, so I'm Nikolaos Stefanovic, and I will present how we organize this shared task 2 with Jacek, Guillaume, and Jakub about fine-grained event classification of news like text snippets. So the context is precisely what classifying text snippets that are about socio-political events. And for this, we use the taxonomy of ACLED. And also we are going to use their data as training data for a classifier. The motivation behind that is that while it's kind of straightforward to build a classifier to using the ACLED data and evaluating it on ACLED data, but this does not give us an understanding of how it works on real data. So that's why the first motivation is the robustness with respect to the data drift that happens when text data has another structure than the training data. Second motivation is the flexibility with respect to the taxonomy, because there are several clients that have overlapping, maybe complementary, and changing taxonomy. So we want to be able to deploy classification models easily for these changing links. And so that's why this shared task has been formula as a generalized zero-shot learning problem. So that means that there is no constraint on the tag set in the test data set. And so we can find there labels that come from the training data, but also one that were totally unseen before. So to give a more concrete understanding of why this is relevant, we took the same event as encoded in ACLED and as taken from the news. So the thing is that often ACLED use almost twice as less characters to describe an event than what will be strictly necessary to have the same information coming from a newspaper. So this is a one difference. Another difference is that ACLED has this kind of fixed structure about date, place, actors, and casualties. While it's not always the case in news, and often there are other stuff related to the publishing journal that needs to be deleted. So this is causing the data feed that we want to be take care of. So the ACLED taxonomy is this one. I guess most of you are acquainted with it. So basically there's 25 subtypes organized along 6 main types. So we are going to build on top of that. So the way we organize the shared task is with 3 subtasks. The first one is a simple classification on this very subtasks that we have just seen. Subtask 2, there are the exact same types that need to be classified, plus 3 unseen types. The thing is that these types were announced in advance, so the participant had the possibility to find additional training data to make some supervised learning. While this last subtask is purely zero-shot, there were these same subtasks as before, plus 2 additional subtasks that were announced on the very day of the release of the test data. So about the test data. So what we did is that we made a data set with about 1,000 text snippets taken from real news articles, about 30 labels, so the accled label plus the new types. The way we did that is by sourcing articles from the web. Then we automatically extracted snippet, cleaned and deduplicated them. And then there were annotations with 2 annotators and several iterations in order to be sure that the data can be classified without ambiguity. And this is a bit of a problem, it appeared, given the accled codebook, but we are going to speak about that at the end. We also added some difficulty by replacing manually some words and expression, and also by making a random perturbation on about 15% of the dataset by changing randomly the toponyms and the dates. So the baseline system here are one simple logistic regression and an hybrid approach for using BERT for the accled types. And when we are dealing with unknown types, how it works is that when the fine-tuned model wasn't sure about the type he has classified, when it was below a given threshold, then we were relying on an NLE-based zero-shot classification using BART. And this has been trained on the dataset as the dataset that we give the reference at the end of this presentation. So the participants. So we had in total 14 teams, 6 of which submitted. And there were 2 phases. So the first phase was before the deadline to submit to the workshop, and the second one finished just a few days ago. So all the systems were transformer-based with several variations, and there will be presentation about most of these later on. So I just want to focus on the fact that only 2 teams used a purely zero-shot based approach for all the tasks. And these are the two teams on the right here. So also, yes, one thing important to take into account here is that each team was training on different data sets. So they had access to ICLE data, but there were a lot of subsamplings, a lot of maybe yes, basically subsampling and not accessing exactly the same data. And so it's not exactly the same data from ACLED, but it's all from ACLED. So when comparing the result, this has to be taken into account. Also, several teams reported that they did not have enough time or resource to train their model to the end. So this also has some impact in some of the results. So here for subtask 1, the first 2 bars, the green one, are the baselines. And the 2 on the right, the yellow and the red, are the purely zero-shot based approach. While all the other ones are transformer-based. So what we can see is that this fine-tuned transformer perform better than zero-shot one, and they performed all of them quite similarly. They were Roberta and BERT-based ones. When we go to the subtask 2, there is a loss in the performance. Here, one team has also been using a few-shot approach that gave better result than this hybrid approach. We still, the purely zero-shot based approach been quite competitive. When we go to subtask 3 with even more non-data types, the performance degrades even more. So the main takeaway, the main result regarding the motivation we highlighted in the beginning. So regarding the performance, the robustness, we consider the performance of the baseline BERT because in the previous paper, it has been evaluated on ACLED data. And here we use the exact same model, but apply to this test data set based on news like text snippet. So what we see is that for micro F1, we have almost, we lose almost 11 points on performance. And one on macro, about 5. So this means that there are a few classes that are more that have more errors, greatly more errors than the other ones. And overall, it shows that it's not possible to just rely on fine-tune solution on artificial data sets, because when we apply it to real data, we have this huge loss in performance. So regarding the flexibility, for this, we look at the performance on the 5 nuancing classes. And unsurprisingly, the performance is worse than what we obtain with fine-tuned models. Also, unsurprisingly, the few-shot model does the best, seconded by the hybrid approach. And interestingly here, the 2 zero-shot, zero-shot based approach perform quite differently. So the one based on NLE classification is the author has reported they didn't have enough time and resource, so this can have could have been an impact on this performance. Still interesting, the one based on can-nearest neighbor perform notably well and also fast as the author reports. So this is also something that is interesting when dealing with real world and real-time applications. So during this this whole shutdown, when we are annotating the data, we run through several shortcomings of the ACLED taxonomy that we thought would be interesting to report here. So we had problem with due to the high specificity of the event description in the ACLED codebook, and often the news does not provide enough information. So for instance, if you know there is a demonstration, but you don't know the level of violence, it's a bit hard to classify this news. Also, there are small nuances in the definition, and still about protest, whether a protest is a violence or there were excessive violence against the protester is something which is quite fine to understand, and it's not so clear. They also spotted some inconsistencies in the database itself. There were also misleading type names because, for instance, the type arrest does not cover all the arrests. So it's very specific, and some arrests are not covered at all by the types. And one thing that's, two things that actually that could be more worrying is that the events are coded with full knowledge of what happened. And it means that it could be that in the text does not appear supporting information to justify the presence of a given label. And lastly, the fact that ACLED is a multi-class classification. So it's an issue because in the news, there are the reports about several aspects of the event, and often about several events at the same time. So multi-label classification will make much more sense, but because it's not possible, there is a very complex and intricate way of classification the information in the codebook. Lastly, to tell you that this dataset has been released and it's available on the GitHub page of the Shatax. Thanks. If you have any question.
We have 2 minutes. 2 minutes for questions. Generic questions regarding the shared task. If there are no questions, I suggest we go to the. Oh, there's a question by Brendan.
Yeah, could you? I'm sorry if I missed this. Would you mind saying briefly again what the relationship is between the new shared task data set to your 2020 paper?
Okay. Nicola, do you want to answer it or should I? Okay.
So basically, the ACLED data set from the calling paper, it consists only of the data that comes from ACLED, that was basically retrieved from ACLED and cleaned, normalized. And what we did here is we basically took news from the web, news snippets, and tried to annotate them with the ACLED, using ACLED taxonomy. That's basically it. And we perturbated them as well in order to make the task a little bit complex. So,
okay. Oh, so the original ACLED data is not naturalistically news text, you're saying?
No, it's not.
Okay.
Well, there was a talk from the ACLED director last year, and from what we understood, most of the data that flows into ACLED is collected by some sort of international liaison officers, but it could be the case that sometimes they cut and paste something from the news, but from what I understood, the vast majority of this data is not cut and paste. It's basically written by a human. And you have to also consider that in the ACLED database, there are different people and they have different styles of coding. So this is I know this much about ACLED.
Makes sense. Thanks.
So I suggest we go to the first presentation in this short session, and I will hand over now to the colleagues from IBM to present briefly their solution.
Great, thank you, Jakub. You can see my screen okay, the full presentation mode? I hope.
Yes.
Perfect, thank you. Yeah, so yeah, let me talk briefly representing the IBM team here on the work we did for task 2. As Nikola described, of course, the task here was to predict the correct classification label for short texts from a list of fine-grained types that the organizers gave us. Here's one more example of that. Here's a text about the SARS outbreak in China in 2002. And for this text, an appropriate label might be the natural disaster label, because when you look at the definition for that class, it includes infectious disease outbreaks. So here also, Nikola already showed this, but the type inventories that we were supposed to classify to, there was the 25 known types for which we had a lot of labeled data, the ACLED data, and then the 3 unseen types and the 2 other types, which I'm calling surprise types because they were foisted on us at the very last minute. I just want to note, though, that I really do like this, this scenario, because I think it mimics a realistic text classification scenario where you've got a bunch of types that you've had since the beginning. There's lots of data for those. So you've been able to train a big supervised model. Then as you use the classifier, maybe new types emerge. But maybe you've seen those for a little while. You've got a little bit of time that you've been able to label a little bit of data for. But then there's brand new types that have just emerged. Maybe you're letting your users, in fact, even generate some types or define new types. So you have no data for those. And then also, as part of these type inventories, we were given definitions. And the definitions were just short glosses for the type, but also they all included these examples, which is going to be important to us going forward. Okay, so let me jump next to the system we built to tackle this. And then later I'll talk briefly about some of the things we learned from participating here. So here's a picture of the system that we built. It takes an input text and it produces a ranked list of event class labels. And for a given text, we don't know whether the best class is going to be from the known types or from the unseen types. So the system needs to be able to predict either. And so we wanted to build one system that did all of them. At the core here, we've got a text classification model. And basically it's a supervised model based on, in our case, Roberta Large fine-tuned on the ACLED data. And then the second main piece is this NLI-based re-ranking model, which is a BERT family model, language model that's been pre-tuned on generic textual entailment data. Let me say a little more about that before getting into the detail of the architecture. So if you were here earlier, Andy gave a talk and he described prompting a natural language inference model to do zero-shot classification, just like we do. It's actually pretty common practice, but I'll recap it quickly here. So the basic idea is you start with a pre-trained language model, your favorite BERT or Roberta, and then you fine-tune it on a whole bunch of textual entailment data. So the textual entailment looks like this. You've got two texts. Text 1 entails hypothesis 1, text 2 contradicts hypothesis 2. Those are kind of examples. And then you fine-tune the PLM on that, and that gives you the NLI model. Usually this data set is the called the multi-NLI or the multi-genre NLI, natural language inference corpus, which has about 433,000 text pairs. Luckily, various people already done this fine-tuning for us. So for the major BERT class PLMs, there are NLI models available off the shelf. So then at inference time, you give the NLI model 2 chunks of text, a context and a hypothesis, and the model gives scores for entailment, the degree to which the context entails the hypothesis, the degree to which it contradicts it or is neutral with respect to it. Of course, it's pretty obvious how you might then turn this into a multi-class zero-shot classifier. You run multiple hypotheses through the model corresponding to the different classes and then normalize their entails scores. Okay, so going back to our architecture here. So here's the example sentence I had on the first slide about the SARS outbreak. The text classification model produces a ranked list of the top known types predicted for this text. You can see natural disaster isn't in there because it wasn't in the training data. And so then if the top scoring class here is below a threshold, we take the top 5 predictions from the classifier and add in the unseen types. And then this bigger set of types will be sent to the zero-shot NLI model for re-ranking. Of course, as I just said, the NLI model can't take class labels, so you need to convert the classes to some kind of textual representation. And then the NLI model gets the original text and the textual representations of the classes and produces the ranked list of the textual representations that are most implied by the original text. So then finally, we convert those textual representations back to the class labels to get a re-ranked set of classes that includes both the known types, of course, re-ranked, and the unknown types. And then for us, the prediction is just the top scoring type comes out of this. Okay, so rather than just report on the results on the eval, I thought I'd look instead at some observations and things we learned during the course of this challenge. So I've chosen 4 in particular. First, a look at how good a model you can train for the classes with this ACLED data. Second, NLI obviously for zero-shot classification is pretty common, but can it also improve a supervised classifier? And then third, NLI for zero-shot, I mentioned this earlier too, is notoriously sensitive to the choice of prompt. So I'll dig into that a little bit. And then finally, does it make sense? Is it a good idea to fine-tune the NLI model? So this slide is all about the supervised text classification. And I think in the interest of time, I'm going to skip over the detail. The bottom line is we basically replicated Jakob's classifier, but using Roberta large instead of BERT base, and got results that were basically consistent with those. We also took our model and further fine-tuned it on a tiny amount of data for the 3 unseen classes. So this is 10% of the ACLED training plus a few examples each for the 3 unseen classes to produce a few-shot supervised model for the 28 classes. But then to make sure that that extra fine-tuning didn't completely hose the performance on the original 25, we ran that experiment and saw that it doesn't actually degrade the performance that bad. Although it did degrade the performance worse on the eval data, which is shown in the green table, than it did on our dev data. Moving on to the NLI model. So obviously we need the NLI model for a zero-shot classification, but does it make sense to run the NLI model to re-rank the output of this classifier, even on the known types? And we contend that it makes sense only if the NLI model is likely to correct mistakes that the classifiers made, but agree with the classifier when it makes the correct predictions. So to test this, we ran a bunch of different NLI models, zero shot, on exactly the instances in our dev data that that really good classifier got wrong. And so that's what this table at the bottom left shows, is that, again, not getting into the details, but depending on which NLI model you choose and how many predictions from the classifier you give it, zero shot NLI can recover 30 to 40% of the mistakes made by this classifier that was already getting 95% accuracy, which is pretty cool. And then on the eval data, not quite so spectacular. We saw a little bump in the F scores when doing zero shot re-ranking of this very accurate supervised model. Okay, yeah, so as we mentioned, the NLI model, it can't deal with class labels. It needs two texts, so you need to convert the classes to textual representations. We experimented with 4 different textual representations, all of them constructed mechanically from the definitions of the classes. So the first obvious one is just use the whole definition itself as the textual representation of the class. And then so you give that as the hypothesis. The NLI model produces a score, which is a measure of how strongly the definition is implied or entailed by the text. And then if you do this for all the classes, you get a ranked list of the most implied class to the least. We also experimented with just the name of the class, since that's pretty common to do with this NLI zero shot, and it didn't work very well. Since all of the definitions had examples in them, we said, let's take the examples, treat them as keywords, and use that as the textual representation. This turned out to be really bad. In fact, this score doesn't show that, but in our experiments, it turned out to be really bad, which surprised us. But then when you think about it, it kind of makes sense that if your text here is about a hacker group, it's going to confuse the model to have in the hypothesis also stuff about assassination and human trafficking. So then we said, okay, well, instead of using all of the keywords as a description, textual representation of the class, let's use each of them independently, what we're calling here disjunctive keywords, and then the score for the class is going to be the maximum score of all of the textual representations of its keywords. And that turned out to be by far the best, so that's what we went with. Here's just some experimental results that we ran on the 4 different, and you can see the wildly different scores that you get just by changing the textual representation. Okay, finally, I mentioned that you can, or I may not have mentioned, but you can use the NLI model off the shelf as it is, or of course you can fine tune the NL model itself to your classes. So we did a bunch of experiments comparing these. The top table, I'm not going to get into, it's just describing how we generated a data set with positive and easy and difficult negative examples in it. But then using this data set, we fine-tuned the NLI model like this. So we took the 24 types, this is the 25 ACLED types minus the other type. We selected 3 at random to hold out as our test set in simulating a zero shot experiment. So then we fine-tuned a model, an NLI model, on all 24 classes and another one on only the 21 without the 3 that are held out. The first row here is just showing you a zero shot BART NLI model off the shelf. It does actually pretty well on the 3 held out classes. The model fine-tuned on all classes, including the 3 held out. No big surprise, does very, very well on the 3 held out. But if you tune the NLI model on classes other than the 3 you're testing on, it does absolutely horrible. But the good news is that the Roberta Large NLI model, off the shelf zero shot with no fine tuning, actually does really well already on completely unseen. So the bottom line here is, well, let me just get to the conclusion since I'm already there. The bottom line on that one is you can fine tune the NLI model if you like, if you know the types that you're going to be classifying or re-ranking, but doing that might make that model unusable for unseen types. And then the other conclusions from those experiments, I'm just basically restating what I already said on those slides. The ACLA data set very well behaved. I think actually it's probably, as Jakob suggested, more regular than natural. There's a lot of repeated language, so it suggests it's a little more template-ish. Another conclusion, as I mentioned, the zero-shot NLA re-ranking is good for zero-shot, but it's also good even on very accurate supervised models to correct the mistakes there. And then finally, takeaway here is that if you're going to use NLI classification for zero-shot, it's really sensitive to the choice of textual representation. And it's a research question on how to know beforehand what's going to make a good representation for previously unseen classes. So that's all I have.
Thank you, Ken. Unfortunately, we don't have time for questions because we are 5 minutes late. So I leave the chat for any questions you might have for Ken. And we will move now to the second presentation by Fraunhofer Institute. The floor is yours.
Hi, thank you. Let me just share my screen. Can you see my presentation?
Not yet.
Okay. How about now?
No. Oh, yes.
Great. Okay, thank
Yes.
you. Is it on full screen now? It should be. Oh.
It's showing presenter mode.
Yeah, I just need to change it. Thank you very much. Okay, that should be better. Okay, so I'm Samantha, and together with my colleague Teresa Krumbiegel, we participated in task 2 of the shared task. We actually only participated in this first subtask, so we did not use any of the unseen classes. We work at the Fraunhofer FKI in Germany, and we actually both have a linguistic background, so most of this talk will focus on the analysis of the data set rather than specifically a model that we chose. So I hope that's okay. This is not. Okay, so I'm going to jump straight into what we did for data collection. So obviously, we also collected data from the ACLED website. And to construct the corpus, we started off by downloading all data from all available regions. And then we very simply removed events with less than 25 tokens and more than 1,000 tokens. We quickly realized that we were not capable of processing all of this data, so we had to make a selection somehow. And we decided to do this by balancing the data set based on the event subtypes present in the data. So originally you can see here that the corpus consisted of about 70% of one specific event and 0.001% of the very lowest one, which I think is chemical weapon. So we decided to extract a percentage of the largest classes based on the distribution and keep all instances for the smallest sub-event types. Then we shuffled all the data to make sure that we did not introduce any region-specific bias, and we selected random samples from the whole data set for training, development, and testing. So you can see here an overview of the final corpus that we used. We had 94,000 training instances, a development set of 9,000 instances, and we created 10 separate test sets, which only contained 2,500 events in total. And you can see here the distribution is still quite skewed, but it was impossible to balance it completely because they are so different in the ACLA data set, but it's definitely better than it was before, and there's only a few outliers in arms clash and peace protest at the moment. And the balance is also the same in the train development and testing set, as you can see with the different shades of gray in the graph. We also created 3 different corpora. We wanted to see the effects of removing certain parts of the ACLED data. So ACLED N contains all of the original text without any modification. So this also still contains all of the ACLED specific information. ACLED L contains a version of the text, but we replaced all locations that we found with the word lock. So we used the Flare NER tagger for this. And ACLED T, we removed all date and time mentions and replaced it with time. We were very curious to see what happened if we remove these very specific markers of events. So we wanted to create these 3 different versions. So the system is very simple that we use, also all based in the FLAIR framework. We submitted 5 systems in total, which were all variations of Roberta and Bert, and each one was trained or fine-tuned using a different version of the corpus. So we have the L, the N, and the T in different ones. I can already tell you that system 2 Roberta, with actually the ACLED without any modifications, was the best model for us. And then more details about this in the paper. We ran some preliminary tests on the 10 different test sets, and this is a range here. So you can see the Roberta ACLED N model achieved a score of 93, but this is using only the 94,000 training instances. So nowhere near as much data as ACLED does actually entail. And then when we evaluated it on the test data from the shared task, we achieved an F1 of 83. So moving on now to, for us, the more interesting part. So generally, for most classes, the performance is pretty good. We also did notice that there's not necessarily correlation between the amount of data available for that specific sub-event type and the performance. So suicide bomb performed particularly well, but it was one of the classes where there was quite little data available compared to what was available for other subtypes. We were more interested in analyzing the classes that did not perform as well. So for all of the different models, we looked at the 2 lowest performing classes, and you can see here that for pretty much all of them, it's either other property destruction and then mob violence as well for the 4th system that we had. So we were interested to see what is actually happening in these specific sub-events. So we started off by doing a very basic analysis of word frequencies to see what's going on in these events. So on the left here, you can see the class suicide bomb, and the most frequent, top 10 frequent words within this class are words like suicide, bomber, killed, attack. So these are words that intuitively you would expect to find in this class. It's also very, very, very homogeneous. There's not much difference in this class. So if we look at other more closely, as we could expect, this is definitely much more, is much less general. So you see things like non and forces and area and displacement, police. So these could also very easily be terms that are present in the other classes as well. So it's not unexpected that the class other would not perform as well, but I think this nicely illustrates the difference. Another observation that we made is that all 5 models very frequently confuse these 2 specific classes, mob violence and property destruction. So we wanted to have a look at why. We do know that these 2 sub-events also belong to one event type of the main 6 main types, so they are bound to be quite close. So what we ended up looking at is the topic compactness for each of these 2 classes. To do this, we created a document embedding per event. And then to look at the topic centroid, we took the average of this and measured the Euclidean distance from each event to the topic centroid. So you can see here that both event types are quite compact. There's not very much difference. There's a few outliers. So you can see here around the 17.5 or 20 mark. But generally speaking, they have a very similar shape when you take into account that they have a different amount of samples. And there's not much difference between the 2. So we wanted to also look at this same analysis, but by combining the 2 topics. So on the graph, you can see light blue and dark blue, but the shape is still very, very similar, and it's still otherwise very compact. So the more compact and to the left of the graph it is, the more compact the topic is too. So this led us to have a look at some specific examples. So the example that we've included on the slides here shows the system predicted that it was mob violence, but it should have been tagged as property destruction. So we both were looking at this and thought that both event types are actually present here. So test instances like this in particular seem to be very, very difficult for models to catch, and also for human annotators as well, to decide if you had to choose only one specific event subtype, which one it would belong to. So we've heard a few comments throughout the other presentations that say something similar as well. So we would like to talk about that further. But if you have any further questions, there's a few more details in the paper, and that's pretty much the main gist of what we discovered for this task. So thank you. Are there any questions?
I can maybe add one thing. In our baseline model based on BERT, as far as I remember, the biggest mismatch was between the two types of protests, protests with intervention and protests with excessive
force. I
force.
think it is.
Yeah, because and also I have to we looked actually at the examples in of the entries in ACLED, and this is just empirical observation, but the entries were inconsistent. So you could see very two similar texts, but one was tagged with police with intervention and another with excessive. But from the text, it was difficult. It would be difficult to infer which is which actually.
Yeah, we had the same problem with these classes specifically as well.
So if there are no questions, I will pass over now to Vani, I believe. I just wanted to say that if anybody from the participants would be interested to work on a future version of this shared task that we organizers really enjoyed, please write us back, because we have some thoughts about future plans. And you know, annotating data is time consuming, so we need people, but also ideas on how to extend it, maybe go multilingual and so on. So now I pass over to Vani. Thank you.
Thanks, Jakub. Can you hear me?
Yes, yeah, I hear you.
I'll try. Okay, I'll share the presentation. Should be. Do you see the slides in presentation mode?
Yeah.
Okay, thanks. I'm Vani Zavarella. I work on the TMECC, so the text mining and analysis competence center of the Joint Research Center of the European Commission. And I'm going to present here the design and some evaluation results from the shared task 3 that we organized for this workshop. So first of all, this is a joint work done together with the colleagues from the University of Pennsylvania, Salvatore Giorgi, and I think is there with us in the workshop, and also Si Huang, that did a tremendous job in providing the input data and also to code the gold standard data set for the Black Lives Matter protests movement, and also with colleagues Nikolaos and Hristo from the JRC, and we also involved the participant teams to provide. They actually provide valuable feedback, because this was a kind of novel, let's say, task. So we actually benefit from their feedback as well. So let's see if I manage to switch this. So the idea, let's say the main purpose of this task was to provide to perform a usability assessment of machine-coded event data for micro-level modeling of social processes, in this case, a protest movement. So instead of doing evaluation on a specific subtask of the whole event extraction process against annotated language data, we actually challenged the systems participating to the task task 1 of this workshop, to process a kind of realistic sample of news and also social media data for this target social protest movement. And then we actually perform a correlation analysis of their overall, the final output of their systems against a human code gold standard for the Black Lives Matter. let's say the correlation analysis was performed in two ways. I will give more details later, but basically we try to capture temporal path. We try to assess whether the system captured the temporal patterns by using protest cell, by basically counting, measuring correlation on protest, what we can call protest cells, which are like geographical units, geographical cells on which at least one protest event was recorded by the gold standard or the system output. And also, while we try to capture, to assess how the system captured the spatio-temporal patterns of the Black Lives Matter by counting, by measuring absolute event counts on space-time units. Where I will give more details about this later on. So first, I want to note that this is a really hard scenario because the input data that was provided to the systems was not overlapping or poorly overlapping with the source that was used in order to code the gold standard. So let's say the baseline for this, of course, was by definition quite low. So it was a very challenging task. Okay, I'll skip here details about the Black Lives Matter process because I guess everybody heard about it at least. I just want to mention here that we focus only on the on a specific time range following basically the murdering of John Floyd on May 25th, 2020, up to the June 30 of the same year. And for this specific time range, actually, this protest movement was actually a very good, challenging use case for this analysis because it was characterized by a fast spreading of very local protest events, unequally distributed over the US country. So as for the input data, we provide actually two types of input data. A non-topic filtered, so generic collection of all news items from the New York Times API for the target time range. This included around 5,000 items, and we provide basically title, abstracts, and publication date as metadata. We also provide a collection of tweets for the same time range, which was collected by Salvatore's team by sampling the Twitter public streaming API using basically three keywords. So Black Lives Matter, All Lives Matter, and Blue Lives Matter. This resulted in around 30 million tweets. And so the systems were expected to access, to use all the whole metadata payload from the tweets. And by the way, this corpus is a subset of a Twitter corpus that was already released and described in Georgi and Al 2020. So a subset for our target time range. The gold standard was made of almost 8,000 manually curated unique protest events for the US territory, because of course the Black Lives Matter spread also outside US. And for the target time range. Event representation was quite simple because we only had one event type, so that was implicit as a protest event basically. And then we include of course date and then a string representation of the location at the city, state, and country level. I don't have time now to give details about the validation process that Salvatore and C went through for coding this data set. I just want to mention that there were two main sources that were used, creosote maps and race and policing, and while at the end a third one was also integrated and deduplicated with respect to them because there was a let's say a low coverage for towards the end of the target time range. This is a visualization of the let's say, of the distribution for the main US territory of the gold standard events, which are the small, I hope it's visible, the small yellow dots, let's say the ones which are more numerous, let's say many. Then while you can also see, we also show there with larger green and red dots, the events automatically recognized, detected, and located by the baselines that we use for this task that we show in a bit. The regular grid, which is like 55 kilometers side, it's the one from the prior grid project, and that's actually the ones that we use for our aggregations, for our spatial or geographical aggregations in the evaluation. So for each type of data, means New York Times, Twitter, and a merge of them. Each participant system was allowed to submit maximum 3 runs. The date format was like 1 line per event, where the event representation was let's say a string representation of the location at the city, region, and country level plus the date. For the purpose of the evaluation, I mean, in order, of course, to do a join with the shape files from the prior grid, of course, we need to convert this string representation of the locations into coordinate pairs, and we did it by query the OpenStreetMap nominatim search API, and we discarded system output event records with no location information, or which return null results in the nominating API. So the evaluation metrics. So first of all, we aggregated events on these geographical cells, basically, and also on time units, which in both types of evaluation were set to day, a single day. Then we basically counts. I mean, we perform 2 kinds of analysis, correlation analysis. A temporal trend analysis, where we consider the total number of activated cells, so test cells for which at least 1 protest event was recorded by the gold standard or the system output, respectively, per time interval, so a day. While in the second analysis that was meant to capture the spatiotemporal trends of the process, we count absolute events. We measure absolute event counts over each single cell day unit, where the cells, where the geographical cells are the same, of course. So these are the ways we derive our variables. For both kinds of analysis, we apply standard correlation. We apply standard correlation coefficients. So the Pearson correlation coefficient R, the Spearman rank correlation coefficient rho, and also error measure. We use the root mean square error. We use 2 baselines, which were probably could not be really defined as a baseline, because these were like well-developed systems. One is Nexus, which is a system that we developed at the GRC. It's a hybrid system, like rule-based, but using machine learned lexical resources. The only thing here worth to mention is that the system was never was not trained on domain corpora in protest movements, for example, and even less on this specific protest movement. We also have a kind of additional baseline, which was basically Nexus coupled with a deduplication post-processing module, which basically combine a geographical distance measure threshold with a semantic distance based on sentence embeddings for the text from which the events was derived. Here I report also a reference to the main paper where the baseline are described. We had 4 participant systems out of the ones that participate in task 1. Of course, there is no time now to give details about the system. Also, because as for the event extraction part they were already described in the previous presentations. For the geocoding part, which is the additional step that the systems had to add in order to perform in this task, they mostly use existing libraries like GeoPy or Spacey. Some of them actually for the event extraction part, there is one system which, interestingly enough, it was like the best performing one. They also integrated a kind of topic filtering, rule-based topic filtering based on curated keywords. So here are on the left, you see that in the left table, on table 1, you see the results with let's say the correlation coefficients and error rates for the total daily protest cell counts. You can see that actually the correlation range from like even negative ones to let's say very weak or weak up to, and only one system actually achieved strong correlation. Interestingly enough, also not many systems managed to outperform the baselines, particularly for the New York Times data, because here you can see we report data about processing from the New York Times articles, Twitter, and also the merge of the two. On the right table, instead, you see the correlation coefficients and error rates for the same settings for the cell day event counts. So these are really like for each geographical cell for each specific day. And here the geographical cell, they range over all the geographical cells in the US territory. Here we count, we measure the correlation on the absolute event counts. And you can see that overall the correlations here drop a lot. Basically, most of the systems, including the baselines in this case, they have very low, negligible correlation with the gold standard. But even in this case, actually, the no-conflict system achieved mostly the best results. Here you also have we show this is actually relative to the first table here on the left, because it's about the total daily protest cells. And you can see that actually both for the New York Times and Twitter, most of the system, all the systems actually fail to capture both, let's say, the temporal pattern of the protest movement, and also let's say so like the evolution, the dynamics, but also let's say the overall size, let's say, of the protest events. You can see that most of the I'm sorry, I forgot to say that the blue in blue you see actually the gold standard, while and you can see that none of the system actually counted more than 100 events, for example, for daily. So there was really like a underrepresentation, let's say, of the process, which was even more significant for Twitter data. Here we report a kind of more lenient way to represent this. This is a confusion matrix between the grid cells that the gold standard system runs code has experienced at least one protest event. As you can see that out of the ones that so the precision in some for no conflict system, for example, is quite high, but the recall is quite low. So out of the gold standard actual protest cells, only a few of them are actually captured by the various systems, as you can see. What lessons we learned from this? We know that was a really hard setup. So systems are being evaluated out of domains in terms of data type, because they were all trained on news data and then evaluated also on Twitter data, and also in the sense of that they were not trained on kind of protest movement context. So in the same contest movement context. For sure, we speculate, but I mean it's kind of probably reasonable to assume that the sourcing affected the low recall, probably because very local protest events from the Black Lives Matter were not reported at all in the New York Times. We expected to be reported somehow in Twitter, so it's actually unclear whether they were not or they were reported, but then the geocoding failure of the participant system and the baselines failed then to locate them properly geographically. But overall, I think the conclusion that we can draw is that more work is needed to be invested in accurate geocoding in order to make automatically extracted event data usable for micro-level analysis of these social movements like Black Lives Matter. And I add here some emails to myself and also to Salvatore teams that they are the ones that have provided the gold standard data, so they are the reference for that. You can also find details about you can also find input data in the link that I report here for the task 3. Thank you, and sorry for I think running a little bit out of time. Sorry.
Thank you very much for all this stuff, not just presenting, doing as well. And for thanks to Salvatore for initiating this effort. It was really great joint work. And I hope we can just make this work even more robust next years.
Yeah, thank you for having me. This was very fun and informative.
It's pleasure. So let's continue with the lightning talks, and if we spare a couple of minutes, I guess 1 or 2 speakers are not here, but in any case, let's start with the lightning talks. And if any question it can about this or previous talks can start either in chat or if we have time later. So do we have the IIIT team for task 1? Pawan, Kalyan, we had some correspondences with Adep Hande. I don't recognize them in the participant list as well. So these guys were like quite late to join the party. They got the data before 2 days before the deadline, and they just submitted competitive system. Therefore, I really would have loved to hear them. Anyway, I think we have Niels, right? On Adepande here, or a co-author of him, right?
Yes.
Perfect. Please present your approach.
So is it visible?
Yeah, we see it. We see your screen.
Yeah, thanks. Good evening to everyone. My name is Cesar Reddy. I am now pursuing an undergraduate.
We only see a gray flat rectangle. Your slides are below somewhere. Maybe you should share the whole screen.
Is it okay?
No, it is a. We have it now.
Yeah.
Perfect. Please start.
Good evening to everyone. My name is Sheikh Reddy. I'm pursuing an undergrad degree at IIT in India. Now I'm going to talk about my research on using pre-trained language models for multilingual product identification, which shows our work on sentence classification subtask at case conference. Now we discussed about dataset. The dataset contains about 28,000 odd sentences in 3 different languages like English, Spanish, and Portuguese. The dataset is divided into 2 categories: event, the sentence that refers to a specific event; non-event, that sentence does not discuss anything about the event. Now let's discuss about the models. We used MBUT, DistilBUT, and Robota models to utilize for the job. MBUT, the pre-trained but multilingual model was utilized, which has 12 layers and 768 hidden heads and 12 attention heads with 179 million parameters. Here we use the MLM and the NSP techniques are employed to pre-train the BUT model. DistilBUT, we use another model named DistilBUT. It is same as because we have three different languages, we use a DistilBUT here. We utilize a cased multilingual DistilBUT model. It has 6 layers and 768 dimensions with 12 attention heads. And another model name is Robota. It has the same design as the BUT, but a different pre-training techniques are used in pre-training. It has 12 layers and 768 attention heads. DistilBUT outperformed all the other models in terms of F1 score. The explanation for this might be that unlike the other 2 models, the Robota model is it is not a multilingual. It is imperative that the performance of voting on all the 3 models has managed to increase the overall score. One of the reasons for the poor performance of the models is imbalance in the distribution of the classes. The data set contains 21 odd sentences which belongs to non-event, and only 4,000 sentences which belongs to event. Our work primarily focuses on fine-tuning language models and feeding them to an architecture we created. We also observed that the problem of the class balance has a significant impact on the performance of the models. Having more event samples could have certainly helped the model distinguishing better among the classes. I think so. Thank you for the opportunity.
Thanks a lot for the presentation and the contribution.
Yeah, thank you.
We should just pass to the FKIE-ITF
yes.
team. Nils, I guess.
I present it.
Thank you.
So, I hope you can see my screen.
We see it.
That's good. So my name is Niels. I'm a student and also work for the Fraunhofer FKIE, and I present our paper using small densely fully connected neural nets for event detection and clustering. In this paper, we participated on the first 3 subtasks of task 1. Our approaches are quite simple, as we use densely connected nets which can be trained very fast. For the first 2 subtasks, we use neural nets with 6 layers and 4 hidden layers. Each of the hidden layers have 64 units. For the first subtask, we use an accumulation of 100 separately trained nets, and each net is trained for 20 epochs. We also use multilingual word embeddings in all subtasks. Yes, and For the second subtask, since we observed that the usage of 100 neural nets has only a marginal impact on the performance, we decided to use only a single net for the second subtask with the same specifications as in the first. For the subtask 1 and 2, we reached for the subtask 1 an average macro F1 score of 0.65. And in the second subtask, we reached a macro F1 score of 0.7. In the subtask 3, we used a quite different approach. First, we trained our net to compare two sentence embeddings, such that we have a function which can compare two sentences. So after the training, our neuronal net can decide whether two sentences belong to the same cluster or not. So for each sentence, we put a node in a graph, and then with a pairwise, when we are predicting, we do a pairwise comparison. And if our neural network predicts that they belong to the same cluster, we add an edge. And if our net predicts that they do not belong to the same cluster, we don't add an edge. Then we analyze this graph we analyze them for disjoint subgraphs, and each disjoint subgraph is then a cluster. With this technique, we reached an conal average score of 0.83. Thank you very much.
Thanks a lot, Nias. Great effort. So do we have Alaaddin, Gural, and or Emin? I don't recognize them in the list. So just moving on. Leo should be around.
Yes.
Yeah.
Show screen.
Yeah.
You should be able to see it now.
Yes, we see it.
Okay, so I'm Leo Buscara, and I represent a joint work between Neuranova and Aix-Marseille University, where we focus on the task 1 of the task of case 2021. And I will speak only about the subtask 4, which is event extraction, as it's a subtask we focus more. For the model we used a rather vanilla model with a pre-trained multilingual BERT and a dense layer with a softmax to predict the classes of each word we want to look at. What we wanted to do is to look at multilinguality, so we only use one model for all the languages, and we train everything at the same time without adding any data or translating any data. And when we look at the size of the training data set we had, we see that we have a lot more events in English and in Spanish and Portuguese. And one of the problems that is known with this kind of models is instability. What we mean by instability is that when you train several times your model with the same hyperparameters and the same data, you can have very different results because of some random seeds that are used inside the model. And we wanted to know to which extent we will have this issue in this work. So we only focuses on two sources of instability. The first one is the training data order. So it's the order in which training data is passed to the model during the learning phase, and the initialization of the dense layer, which predicts the classes. And what we see here that we have, so we took the training test, we separated in 3 different parts, 60% for training, 20% for validation, and 20% for tests. And here are the results after 20 different training of 40 epochs. And what we see is that for English, we don't have a lot of differences on the test results between the worst score and the best score. Whereas in Spanish and Portuguese, we have huge differences between the results we have. For Spanish, it's above 1.2 F1 score, which is really a huge discrepancy. And that's an issue because we want to have a model that will always learn in the right way, and not we don't want to look at the lucky model to have the best results. And so we tried several things to diminish these instabilities, which didn't work. But what we saw is that instability is an issue for this kind of model, but there is some hope, especially one of the issue is the initiation of the dense layer, and you have ways to find good initialization for this dense layer by trying to fine-tune your model and your dense layer on a task which has the same output, and taking the dense layer as base instead of a random one. And so our code is available on GitHub, and you can find all the other information and the experiment we've done in the paper.
Thanks a lot, Leo. We can pass to Ben. Are you there?
Yeah, I'm here. Can you see my screen?
Yeah, we see it.
All right, excellent. So I'll try to be fast. I'm Ben Radford. I'm at UNC Charlotte, and I did task 2. So I took a very similar approach to the IBM team. In particular, I'm doing like an entailment model or a natural language inference type model. So an input example in how I process the data, I would just take the text, like the actual sentence you're trying to classify, and then append the class to the end of it. And then the goal of the model is just to output 1 or 0, true or false, or a number between 0 and 1, and then I'd round it. All right, cool. So to get positive and negative examples to train this model, I just use negative sampling, right? So I took all of the true examples from ACLED and I made positive examples, and then I took all of the incorrect classes and I paired them up with all of the true sentences, and I made incorrect or negative samples. And the model's goal is just to discriminate between these two. Okay, so unlike the IBM approach, I kind of took like a simpler, a lazier approach. I input the text into a pre-trained Roberta model. I just take the output of the hidden states, I max pool those, and then I pass them through a single dense layer to predict 1 or 0. So I did no fine tuning on like any kind of NLI data sets that are out there. The only fine tuning was done on the ACLED data for the in-sample classes. And so the question is, does it work? And the answer is basically not great. So in sample classes, like test set, but in sample, it does okay with an F1 of 0.74, which a few years ago would have been great, but now is, it's all right. And out of sample, it doesn't work very well, except for a few classes. Diplomatic events, it seems to do pretty well on, but the others, it does not do very well. And that's it. Thank you.
Fast. Thank you very much. Yeah, it works. I understand it. Thank you very much, Ben. So the last lightning talk is from Sabancı University, Furkan Çelik, or Fatih Beyhan or Reyhan Terzi, Yeni Terzi should be around.
Hello.
Hi.
Can you see my screen?
Yes.
Okay. Hello, my name is Fatih. I'm a master's student. Furkan and Tuberk were senior undergrad students and did this project as their senior graduation project. We participated as a Sabancı University Natural Language Processing Group in all 4 subtasks in English. We tried various architectures for each subtask, and I'll be summarizing those in a short way right now. For subtask 1 and 2, they were pretty much the same task with different input lengths. Hence, we used the same approach for subtask 1 and 2. The models we have tried was CNN, LSTM, GRU, BERT, Roberta, and Albert. Additional to these models, we tried another model, which is called CNN LexStem model. This is basically a multi-channel CNN with lexical and stem version of the words. The main motivation behind this model was making our model more generalizable. Hence, some of the events has different tenses. And finally, we tried weighted ensemble model with confidence intervals. You can see that LexStem models improve the results on the left table. And on the right, you can see the improvement of scores with our ensemble models. In this subtask, we implemented a mention pair model. It's a basically 2-step approach. The first step is classification, and the second one is clustering. On the classification part, we used BERT, Roberta, Albert, an ensemble of these 3 models. On the clustering part, we just used approach of Urs et al. From last year, 2020. And additionally, we explored the effect of dataset size by extending our dataset, which is case 21 dataset, with the previous year's dataset, which is SPAN 20 dataset. And on the left, you can see the classification results. BERT and ensemble model did the best 2 jobs. Hence, we used those 2 models to make our submissions, final submissions for clusters. And on the right, you can see that extended model improved the results for BERT and ensemble. In subtask 4, which is a sequence labeling, we used BERT and Roberta as our baselines. And then we implemented BiLSTM CRF heads for our transformers to get some improvements. On the table left, you can see that BiLSTM CRF had actually improved results, especially for the BERT. And we analyzed our individual tag performances. We have seen that our model did a better job at identifying the triggers compared to its arguments. We suspect that this is happening due to high numbers of triggers compared to arguments number. While we took the 5th place for subtask 3, for subtask 1 and 2, we achieved the 3rd place. We had a submission issue with subtask 4, but after the deadline, we did our submission, and we have seen that we could have taken the 2nd place if we didn't have any issues. Please see our paper for more details. You can also see our code in the GitHub repo, which is right here. If you have any questions, please feel free to send an email. That's all. Thank you for listening.
Thanks a lot, Fatih. It was a great summary. And the Sabancı team is the Urs et al. Actually, people who started to work in this subtask 3. So we really appreciate their commitment and help and all this stuff. So this is the end. Thank you very much to all organizers, all correspondences, submissions, ideas, and hope to make it even better next year. Please just contact any of the organizers. Our contact information is on the proceedings, and keep in touch. Bye-bye.
Thank you.
Thanks, Ali. Thanks, everyone.
Thank you.
Thanks. Bye.
Bye.
Thank you. Bye-bye.
You too. Bye-bye.
Bye.